The universe is not expanding into anything, and that might be the most unsettling sentence you hear all year. For 13.8 billion years, space itself has been growing, stretching, pulling galaxies apart at speeds that defy everything your senses tell you is possible. Right now, the observable universe measures 93 billion light-years across. That number gets bigger every second you spend reading this. And here is the part that breaks most people. There is nothing outside of it. No room it is growing into, no container holding it, no blank canvas waiting to be filled. The universe is not like a balloon inflating into a larger room. It is the room. It is making the room. It is the only room there has ever been. Before the Big Bang, there was no space. No time, no void, not even emptiness. The word before may not even apply because before requires time, and time did not exist yet. So when cosmologists say the universe began from a point smaller than an atom, they are not talking about a tiny object sitting in empty space. They are talking about space itself being born. And this is where the paradox lives. How can something expand if there is nowhere to expand into? How does the ground beneath existence get laid down in the first place? And what does it mean that the universe is not filling space, but creating it, one Planck length at a time, as it grows? These are not philosophical questions, they are not thought experiments. They are the direct consequences of observations made by the most precise instruments humanity has ever built. Instruments that have forced physicists to abandon nearly every intuitive idea we once had about where we are, what we're inside of, and whether the word outside even makes sense anymore. This is that story. Welcome to Spacedust. If you're new here, please subscribe. We make these documentaries every day and we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in for a great journey. You have been alive for exactly 0 seconds of a universe without time. You have stood in exactly 0 places that were not already space. And you have experienced exactly 0 moments of true absolute nothing, which makes you, and every human who has ever tried to understand where the universe came from, catastrophically unqualified for the job. This is not an insult, it is a statement of fact. Your brain, every neuron and synapse, every pattern of thought you have ever had, evolved inside a universe that already existed. You think in terms of before and after because time has always been running. You think in terms of here and there because space has always been available. You think in terms of something and nothing because even when you imagine an empty room, you are imagining a room, 4 walls, a floor, a ceiling, air molecules drifting in the silence. That is not nothing. That is a mostly empty container, and the container itself is something. True nothing does not have walls. It does not have dimensions. It does not wait quietly in the dark, patient and still, ready for something to arrive. True nothing, the kind of nothing that might have preceded the Big Bang, is not a void you could float through. It is not a blank canvas. It is not even black because black is a colour, and colour requires light, and light requires space, and space is exactly the thing that does not exist yet. The word itself fails. We say nothing, and our minds conjure an image, some empty field or a stretch of silence, but that image is already cheating. The moment you picture it, you have added space back in. You have added time. You have smuggled in the very things you were supposed to leave behind. And this, right here, is why 13.8 billion years after the universe began, we are still arguing about what that sentence even means. Because if the Big Bang marks the beginning of space and time, then the question what came before stops making sense. Before is a word that requires time. It means earlier on a timeline. But if time itself starts with the Big Bang, then there is no earlier. There is no moment sitting 1 second back or 1 billion years back waiting to be examined. The timeline does not extend backward past that point. It does not fade into fog or mystery. It ends. Hard stop. No prologue. And if space itself begins with the Big Bang, then the question, what did the universe expand into, also stops making sense. Into implies a container, a surrounding region, an exterior. But if space is what the Big Bang creates, then there is no exterior. The universe is not expanding into a pre-existing emptiness. It is not inflating like a balloon inside a larger room. The balloon metaphor, which everyone uses and everyone hates, fails exactly here. Because when you picture a balloon inflating, you picture it sitting in a room. You picture air outside the balloon. You picture space around it. The universe does not have that. There is no around. There is no outside. The expanding universe is all the space there is, and it is making more of itself as it goes. This is where human intuition goes to die. Because everything in your experience tells you that if something is expanding, it must be expanding into something. Your lungs expand into your chest cavity. A city expands into the surrounding countryside. Even an explosion, the metaphor everyone reaches for and every cosmologist begs you to abandon, expands into the air around it. But the universe is not exploding outward into space. It is not moving through anything. Space itself is stretching. The fabric, the grid, the stage on which everything happens is getting bigger. And there is no stage underneath that stage. You can sit with that for a while. You should. Because the discomfort you are feeling right now is not a sign that you are failing to understand. It is a sign that you are starting to. The idea is supposed to feel impossible. It is supposed to twist your brain into a knot. You're trying to imagine a state that by definition cannot be imagined, using a mind that was never built for the task. And yet here we are, trying anyway. The ancient cosmologies understood this problem better than we give them credit for. They did not have the math. They did not have telescopes or particle accelerators or the cosmic microwave background. But they understood that the origin of everything is not a question you answer with data alone. It is a question that sits at the edge of language, where metaphor and meaning start to blur. The Sumerians, 4,000 years ago, described the beginning as a time when heaven and earth were not yet separated, when names had not been assigned, when nothing had been called into being, not a void exactly. More like a state of undifferentiation, everything and nothing at once, waiting to be divided into the pieces we recognize as reality. The ancient Egyptians told a story about a primordial ocean called Nu, dark and formless, existing before the gods, before the sun, before the world. The first god rose from Nu like an island breaking the surface of a vast sea. Creation was not making something from nothing. It was separation, ordering chaos into structure, pulling form out of formlessness. The Greeks, when they finally turned their attention to the question, brought a different tool, logic. Anaximander, writing in the 6th century BCE, proposed the apeiron, a term that translates roughly as the boundless or the indefinite. Not nothing, not something, a kind of infinite potentiality from which the ordered cosmos emerged. He did not claim to know what the apeiron was made of, or whether it had been there forever, or whether it had a cause. He simply said that something boundless and undefined must have preceded the structured world we observe. He could not prove it. He could only point at the universe and say this did not come from itself. The idea of absolute nothing, the kind philosophers would later call ex nihilo, out of nothing, does not show up cleanly in these early cosmologies. Even the creation myths that describe a beginning tend to start with something. A void? Yes. A darkness? A chaos? But not non-existence. The absence of all things, including the absence itself, is an idea that took centuries to articulate clearly. And even now, when we finally have the language and the mathematics to describe a universe emerging from a state with no space, no time, no matter and no energy, the idea remains just as slippery as it was for Anaximander. Because nothing is not a thing. You cannot put it under a microscope. You cannot measure its properties. You cannot say it has a temperature or a density or a duration. The moment you assign it any quality at all, it stops being nothing. And yet we talk about it constantly. We say the universe came from nothing, and half the room nods while the other half objects, and both sides are using the word to mean something different. When physicists say nothing, they usually mean a quantum vacuum. A state with no particles, no matter, no light, but still governed by the laws of quantum mechanics. A vacuum in this sense is not empty. It seethes with virtual particles popping in and out of existence, borrowing energy from the future and paying it back before anyone notices. It has structure, it has rules. It is absolutely not the kind of nothing a philosopher means when they talk about non-existence. When theologians say nothing, they mean the absence of anything that could be called a natural cause. No laws, no fields, no quantum fluctuations. a state so empty that even the potential for physics does not exist. That kind of nothing is, by definition, outside the reach of science, because science studies how things behave, and behaviour requires things. And when most people say nothing, they mean an empty room. Darkness, silence, a blank slate waiting for something to be written on it. That is not nothing either. That is a vacuum in the everyday sense, a container with the contents removed. Still a container. The question of what happened before the Big Bang runs headfirst into all three definitions at once, and survives none of them. If time began with the Big Bang, then there is no before, and the question dissolves. If time existed beforehand in some larger framework we have not yet mapped, then the Big Bang is not the beginning of everything. It is just the beginning of this universe, this region, this chapter. And if time itself is meaningless in the state that preceded the Big Bang, then we do not even have the grammar to ask the question properly. Cosmologists have tried to sidestep the whole mess by saying the Big Bang marks the boundary of physics, not because something magical happened there, but because the equations break down. General relativity, the theory that describes gravity and the shape of spacetime, runs into a singularity at the moment of the Big Bang, a point where density becomes infinite, where temperature becomes infinite, where the math spits out nonsense and refuses to go further. That singularity is not a place. It is not a moment you could visit if you had a time machine. It is a signpost that says the theory has reached its limit. Beyond here, you need new tools. Quantum mechanics might provide those tools, or it might just replace one set of infinities with another. The truth is, no one knows what happens when you try to describe the origin of space-time using the laws of quantum mechanics, because we do not have a complete theory of quantum gravity yet. We have sketches, we have candidates, string theory, loop quantum gravity, a dozen other frameworks that might work or might not, but none of them have been tested. None of them make predictions we can go out and check. They are ideas waiting for evidence, and evidence about the first fraction of a second after the Big Bang's in short supply. What we do have is the cosmic microwave background, the faint afterglow of radiation from when the universe was 380,000 years old. We can see back that far. We can measure the temperature, the lumpiness, the slight variations in density that eventually grew into galaxies. We can use that data to work backward, reconstructing what must have happened earlier. And when you run the equations in reverse, you get a universe that was smaller, hotter, denser, until finally you reach a point where the entire observable universe, everything we can see in every direction, was compressed into a region smaller than an atom. That is not poetic language. That is the actual prediction. A sphere of space containing all the matter and energy that would one day become 400 billion galaxies, packed into a volume so small you could not see it with the naked eye even if you were standing next to it. And then, for reasons we still do not fully understand, that tiny region started expanding, not exploding, expanding. The space itself stretched, carrying the matter and energy along with it, inflating at a rate so extreme that within a fraction of a second it had grown larger than a galaxy. The first moments of the universe were not slow, they were not gentle. They were a runaway process, an exponential surge called inflation that smoothed out the wrinkles and set the stage for everything that came after. But why did it start? What triggered the expansion? If the universe was sitting there, compressed into a point perfectly stable, why did it suddenly decide to become something else? One answer is that it was never stable. Quantum mechanics does not allow stability at that scale. At the smallest distances, at the highest energies, everything fluctuates. Particles appear and disappear. Fields jitter and spike. Empty space, if you zoom in far enough, is a chaotic mess. And if spacetime itself is subject to those same quantum fluctuations, then a tiny seed of space could spontaneously inflate, much the way a bubble forms in boiling water. Not because something pushed it, because the conditions made it inevitable. That is one story. There are others. Some involve colliding brains in higher dimensional space. Some involve a previous universe collapsing and rebounding into a new Big Bang. Some suggest the universe is eternal, cycling through endless expansions and contractions, with no true beginning at all. Each story solves one problem and creates two more. Each requires assumptions we cannot test, and each leaves us exactly where we started, staring at the same basic question. Where did it all come from? The paradox is this. If the universe had a beginning, something must have caused it. But causes happen in time. They require a before and an after. If time itself began with the universe, then there is no before, and the concept of a cause stops making sense. You're left with an event that happened for no reason, or you're left with a reason that exists outside time, which is just another way of saying you do not know. If the universe did not have a beginning, if it has simply always existed in some form, then you avoid the problem of creation, but you inherit a different problem, an infinite past, an endless chain of moments stretching backward forever, with no starting point. That is not easier to picture than a beginning from nothing. It is just a different flavour of impossible. And if the universe is part of something larger, a multiverse where big bangs happen routinely, like bubbles forming in an infinite ocean of quantum foam, then you have only pushed the question back one level. Where did the multiverse come from? What are the rules that govern it? And why those rules instead of others? Every answer leads to another question. Every explanation requires an explanation. And at the bottom of it all, underneath every theory and every equation, sits the same stubborn fact. Something exists, you exist, the universe exists, and existence itself is the thing that needs explaining. This is not a problem science can solve by building a better telescope or smashing particles together at higher energies. Those tools can tell us how the universe behaves. They can map its history, measure its age, trace its expansion back to the earliest moments we can observe. But they cannot tell us why there is something rather than nothing. That question sits at the boundary between physics and philosophy, in a region where evidence runs out and intuition takes over. And intuition, as we have already established, is not up to the task. The ancient Greeks knew this. They built elaborate cosmologies, filled with spheres and epicycles and perfect circles, trying to explain the motions of the stars. And every time they looked closer, they found more complications, more layers, more questions. The universe, it turned out, was not simple. It was not built for human comprehension. It was built according to rules we had to discover one painful step at a time, and every step revealed how much farther we still had to go. We are still taking those steps, still discovering, still arguing. And the question that started it all, the question every human culture has asked in one form or another since language began, remains as unanswered now as it was 4,000 years ago. What happened before the beginning? The next chapter tries to answer that by describing the moment itself, not before, not after. The precise instant when the universe went from not existing to existing, or from existing in one form to existing in another. A point smaller than an atom, hotter than anything we can measure, denser than anything we can imagine. The seed from which everything grew. If you thought nothing was hard to picture, wait until you try to wrap your head around that. The universe is not 13.8 billion years old because someone counted backward. It is 13.8 billion years old because the light we see from the farthest galaxies has been travelling for that long, stretched and redshifted by the expansion of space itself. Because the cosmic microwave background, the faint afterglow of radiation that fills every corner of the sky, matches the predicted temperature of a universe that has been cooling for exactly that amount of time. Because when you measure the abundances of hydrogen and helium in the oldest stars, the ratios line up with what nuclear fusion should have produced in the first few minutes after everything began. The age is not a guess. It is the number that falls out when you run the equations forward and backward, cross-check them against observation, and find that the same answer keeps showing up no matter which method you use. And if you run those equations backward far enough, they all point to the same impossible conclusion. 13.8 billion years ago, the universe was not just smaller. It was unimaginably, incomprehensibly smaller. The entire observable cosmos, every galaxy cluster, every star, every atom that would eventually make up planets and people, and the chair you're sitting in right now, was compressed into a region of space so tiny that calling it microscopic would be a generous exaggeration. We are talking about a scale smaller than a single atom, smaller than a proton, smaller than anything you could ever hope to see, even in principle, because the wavelength of light itself would be too large to fit inside it. This is the initial singularity, the point from which, according to general relativity, everything began. Not a point sitting inside space, a point that was space, all of it. compressed into a volume so small that the equations describing it stop making sense and spit out infinities, infinite density, infinite temperature, infinite curvature of spacetime. Mathematicians have a word for when a calculation produces infinity as an answer. They call it a breakdown, a sign that the model you are using has hit its limits. And that is exactly what happens when you try to describe the universe at the moment of the Big Bang using Einstein's equations. The math does not fail because Einstein was wrong. It fails because general relativity was never designed to handle conditions that extreme. It is a tool built for describing planets and stars and galaxies, not the birth of space-time itself. So when cosmologists talk about the singularity, they are not describing a physical object that actually existed. They are describing the boundary where their best theory runs out of road. A signpost that says, beyond this point, you need quantum mechanics. You need a theory of quantum gravity. You need something we do not have yet. But even without a complete theory, we can describe what happened next. Or at least, what the evidence says happened next. Because while the singularity itself may be a mathematical abstraction, the aftermath is not. The expansion is not. The cooling is not. The formation of particles, atoms, stars, galaxies, all of that is written into the structure of the universe we observe today. The cosmos is a fossil record of its own birth, and we have learned how to read it. Start with the Planck epoch. The first 10 to the minus 43 seconds after the universe began. That number is so small it does not fit comfortably into human language. It is a decimal point followed by 42 zeros and then a 1. 1/10,000,000th of a trillionth of a trillionth of a trillionth of a second. At that scale, time itself becomes grainy. Quantum effects dominate. Space and time stop being the smooth continuous fabric we experience in everyday life and start behaving like a jittery fluctuating foam. Physicists call this quantum foam, and it is not a metaphor. It is a prediction that falls out of the math when you try to combine quantum mechanics with general relativity at the smallest possible distances. During the Planck epoch, the universe was not just hot. It was hotter than anything we can produce in a particle accelerator, hotter than the core of any star, hotter than a supernova. The temperature was so extreme that particles as we know them could not exist. No protons, no neutrons, no electrons, just a seething plasma of energy and quantum fields, fluctuating wildly, governed by laws we can only guess at. The four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, may have been unified into a single force, or they may have already begun to separate. We do not know. We cannot know, because we have never observed matter at those energies, and we have no way to recreate those conditions in a lab. What we do know is that the Planck epoch did not last long. It could not. The universe was expanding, space itself was stretching, and as it stretched, the energy density dropped. The temperature dropped, and as the temperature dropped, the forces began to decouple. First, gravity split off, becoming the distinct force we recognize today. Then, the strong nuclear force. Then the electromagnetic and weak forces separated, locking into the forms they still hold now, 14 billion years later. This is called symmetry breaking, and it is one of the most important processes in the early universe. When the forces were unified, the laws of physics looked the same in every direction. Perfect symmetry. But as the universe cooled, that symmetry shattered, and the forces took on distinct identities. Think of it like water freezing into ice. Liquid water looks the same in every direction. It has no preferred orientation, but when it freezes, the molecules lock into a crystal structure with specific angles and patterns. The symmetry is broken. The ice has a shape. The same thing happened to the universe. As it cooled, the underlying fields that give particles their mass and properties locked into place, and the cosmos took on the structure we see today. Then came inflation. This is where things get strange. And by strange, I mean stranger than everything that came before, which is saying something. Inflation is the hypothesis that sometime between 10 to the minus 36 and 10 to the minus 32 seconds after the Big Bang, the universe underwent a period of exponential expansion. Not fast expansion, exponential. The difference matters. Fast means the universe grew quickly. Exponential means it doubled in size, then doubled again, over and over. In the span of time it takes light to cross the width of a proton. In less than a trillionth of a second, the universe grew from a scale smaller than an atom to a scale larger than a galaxy. That is not an exaggeration. That is the actual prediction. Space expanded faster than the speed of light. Not because anything was moving through space faster than light, which is still impossible, but because space itself was stretching. The speed limit of light only applies to objects moving through space. It does not apply to the expansion of space itself. Space can do whatever it wants. And during inflation, what it did was balloon outward at a rate that makes every explosion you have ever seen look like it is standing still. Why did this happen? The short answer is, we are not entirely sure. The leading explanation involves a field called the inflaton, a hypothetical quantum field that filled the early universe and drove the expansion by sitting in a high energy state, much like a ball balanced at the top of a hill. While the field stayed at the top of the hill, its energy acted like a repulsive force, pushing space apart. Eventually the field rolled down the hill, the inflation ended, and the energy that had been driving the expansion converted into particles. Matter, radiation, the raw ingredients for everything that came after. That conversion process is called reheating, and it marks the end of inflation and the beginning of the hot Big Bang phase. The universe was still unimaginably hot, still unimaginably dense, but it was no longer inflating, it was simply expanding in the ordinary sense. Growing larger, cooling down, allowing particles to form and interact according to the rules of physics we can actually test in a laboratory. Here is what inflation solves. Without it, the Big Bang model has a few uncomfortable problems. One of them is called the horizon problem. When we look at the cosmic microwave background, the radiation left over from when the universe was 380,000 years old, we see that it has almost exactly the same temperature in every direction. The variations are tiny, less than 1 part in 100,000. That uniformity is strange because regions of the sky that are on opposite sides of the universe, separated by billions of light years, have never been in contact with each other. Light from one region has not had time to reach the other. So how did they end up at the same temperature? How did they know to match? Inflation solves this by saying that before inflation, those distant regions were close together, close enough to exchange energy, reach thermal equilibrium and settle on the same temperature. Then inflation stretched them apart faster than light, so that by the time we see them today, they look like they have never communicated. But they did. They just did it before the universe expanded by a factor of 10 to the 26 or more. Another problem inflation solves is the flatness problem. The geometry of space, on the largest scales we can measure, appears to be almost perfectly flat. Not curved like the surface of a sphere, and not curved like a saddle, just flat. That is weird because general relativity says the curvature of space depends on the density of matter and energy inside it, and there is no reason the density should be tuned to the exact value needed to make space flat, unless inflation happened. Because inflation stretches space so much that any curvature it might have had at the start gets smoothed out, the way wrinkles disappear when you stretch a sheet of rubber tight. After enough stretching, space looks flat, even if it was not flat to begin with. The evidence for inflation is indirect but compelling. The cosmic microwave background has a specific pattern of tiny fluctuations, hot spots and cold spots, that match the predictions of inflation models almost exactly. Those fluctuations started as quantum jitter during the inflationary epoch, tiny random variations in the density of the inflaton field. Inflation stretched those quantum fluctuations to cosmic scales, freezing them in place as slightly denser and slightly less dense regions of space. Later, gravity took over. The denser regions attracted more matter, collapsed into gas clouds, formed stars, built galaxies. The cosmic microwave background is a snapshot of those density variations when they were still just ripples. And the pattern we see matches what inflation predicts. Not loosely, precisely. That does not mean inflation is proven. There are competing models, there are variations on the basic idea, and there are cosmologists who think the whole framework is too flexible, too easy to tweak to match any data. But right now, inflation is the leading explanation. It fits the evidence, it solves real problems. And no one has come up with a better story that does not require even stranger assumptions. So picture this. The universe starts as a singularity, or something very much like one. a state of such extreme density and temperature that space-time itself becomes quantum, foamy, unstable. Gravity splits off from the other forces, the strong force decouples. And then, for reasons tied to a field we have never directly detected, space undergoes a runaway expansion. The entire observable universe, everything we will ever be able to see, inflates from a region smaller than a grain of sand to a region larger than a galaxy in less time than it takes light to cross a single atom. The expansion ends, the energy driving it converts into particles, and from there the ordinary Big Bang takes over. The universe continues expanding, but at a much slower rate. It cools. Particles combine into protons and neutrons. Protons and neutrons combine into hydrogen and helium. Matter spreads out. Gravity pulls it back together. Stars ignite, galaxies form, planets condense from the debris. And 13.8 billion years later, you're sitting here, made of atoms forged in the cores of dying stars, trying to wrap your head around how any of this could have happened. Now let's address the misconception that refuses to die, no matter how many times scientists correct it. The Big Bang was not an explosion. It was not a bomb going off at the centre of space, flinging matter outward into a pre-existing void. There was no centre, there was no void, there was no outside. The Big Bang describes the expansion of space itself, everywhere at once. Every point in the universe was part of the initial state. Every point expanded. If you could somehow rewind time and watch the universe shrink back down to the size of an atom, you would not see all the galaxies rushing toward a single point in the middle of space. You would see space itself contracting, distances between galaxies shrinking, the fabric of the cosmos folding in on itself until finally there was no fabric left. Just the singularity, everywhere. When space expands, it does not push matter apart the way an explosion does. It stretches the distance between objects. Imagine a sheet of rubber with dots drawn on it. If you stretch the rubber, the dots move farther apart, but the dots themselves are not moving through the rubber. The rubber is moving. The space between the dots is increasing. That is what the expansion of the universe is doing. Galaxies are not flying away from us through space. Space is growing, and the galaxies are being carried along for the ride. This is why distant galaxies can recede from us faster than the speed of light without violating relativity. They are not moving through space faster than light. Space itself is expanding between us and them. The speed limit applies to motion through space, not to the expansion of space. And during inflation, space expanded so fast that regions which had been neighbouring patches of quantum foam ended up separated by distances light could never hope to cross, no matter how long it travelled. The phrase "smaller than an atom" is not poetic license. It is the result of running the equations backward. If the observable universe today has a diameter of about 93 billion light-years, and if space has been expanding at known rates for the past 13.8 billion years, then at earlier times, everything we can see was packed into a smaller volume. 1 billion years after the Big Bang, the observable universe was about a tenth its current size. 1 million years after the Big Bang, it was a thousandth. 1 second after the Big Bang, it was smaller than the solar system. 1 microsecond after, smaller than the Earth. Keep going, and you reach a point where the entire observable cosmos fits inside a region the size of a grapefruit, then a marble, then a grain of sand, then smaller, smaller, until you hit the Planck scale where quantum effects take over and classical spacetime stops making sense. That final stage, the Planck scale, is not something we have observed, it is something the math points to. A prediction of general relativity pushed to its absolute limit, and at that limit, the theory tells us it can no longer be trusted. Because general relativity does not include quantum mechanics, and quantum mechanics becomes unavoidable at scales that small. The singularity is where the two great theories of 20th century physics, general relativity and quantum mechanics, collide, and neither one knows what to do. This is not a failure of science, it is a map. A clear statement of how far our current understanding reaches and where the boundary lies. We know how the universe behaves from the end of inflation onward. We can describe particle interactions, nuclear fusion, structure formation, all the way up to the present day. We know less about the inflationary epoch itself, but we have models that fit the data and make testable predictions. The Planck epoch, the singularity, the state before inflation, those are still guesses. Educated guesses, built on solid physics, but guesses nonetheless. And that is fine. That is how science works. You map the territory you can reach, you make predictions about the territory beyond, and you keep looking for ways to test those predictions. The moment of creation, if we can call it that, was not a moment in the ordinary sense. Time itself was part of what began. The singularity did not sit in time, waiting to explode. Time and space emerged together, tangled up in a quantum state we do not yet have the tools to fully describe. And yet, from that state, or from something very much like it, the universe grew, expanded, cooled, structured itself, became everything. You're made of particles that were forged in stars. The stars were made of hydrogen and helium that formed in the first few minutes after the Big Bang. The hydrogen and helium were made of protons, neutrons and electrons that condensed out of a quark-gluon plasma as the universe cooled. The quark-gluon plasma came from the energy released at the end of inflation. And inflation came from a quantum field rolling down a hill in a space smaller than anything your mind can comfortably hold. Every atom in your body is a fossil from the first second of time. Every breath you take contains particles that were there, in some form, when the universe was too hot for atoms to exist. You're not separate from the Big Bang. You're part of its expansion, a temporary pattern in the field of energy that began stretching 13.8 billion years ago and has not stopped. The moment of creation, as much as we can reconstruct it, was not an explosion in space. It was the birth of space, the ignition of time. The beginning of expansion that is still happening right now, in the space between your eyes and this screen, in the gap between galaxies, in the fabric of the cosmos itself. Space is not a container. It is not a stage. It is a thing, a dynamic, flexible, expanding thing. And understanding that, really understanding it, changes the entire question of what the universe expanded into. Because it did not expand into anything, it expanded, full stop. And the implications of that, the way space behaves as a substance in its own right, is where the next part of the story begins. Space is not what you think it is, and that is not a setup for a metaphor. It is a direct statement about the most basic misunderstanding humans carry around in their heads every day of their lives. You think space is emptiness, a gap between things, the nothing that sits between your hand and the wall, between the Earth and the Moon, between one galaxy and the next, a passive background, a stage where the real action happens. You think space is what is left over when you remove all the objects from a room. You are wrong. And you are wrong in a way that makes it nearly impossible to understand how the universe actually works. Because space is not a gap. It is not a background. It is not the absence of stuff. Space is a thing. A physical, dynamic, flexible thing that bends and stretches and ripples and grows. It has properties. It responds to the presence of matter and energy. It can be measured. It can change. And most importantly for this story, it can expand. Not by stretching into some pre-existing void, but by creating more of itself as it goes. This idea, the idea that space is something rather than nothing, took humanity a very long time to arrive at. For most of history, space was assumed to be exactly what it looked like: empty, inert, fixed. A cosmic grid that objects moved through, unchanging and absolute. Isaac Newton built his entire system of physics on that assumption. In Newton's universe, space was a container. Time was a clock. And both ran independently of whatever happened inside them. You could remove every star, every planet, every atom from the universe, and space and time would still be there, ticking along, perfectly indifferent. Albert Einstein destroyed that picture in 1915 with a theory called general relativity. And what he proposed in its place was so strange, so fundamentally at odds with human intuition, that even now, more than a century later, most people have never fully absorbed what it means. Einstein said that space and time are not separate. They are woven together into a single four-dimensional fabric called spacetime, and that fabric is not rigid, it is flexible. It bends in response to the presence of mass and energy. A planet sitting in space does not pull on other objects with some mysterious force reaching across the void. It warps the spacetime around it, creating a dip, a curvature, and objects moving nearby follow the curved paths through that warped geometry. Gravity is not a force in Einstein's picture, it is the shape of spacetime itself. That alone would have been revolutionary. But Einstein went further. He said that space-time does not just sit there, passively curved by the objects inside it. It can stretch, it can contract, it can ripple like the surface of a pond when a stone is thrown in. Space-time is dynamic, it evolves. And the equations that describe its evolution, the Einstein field equations, predict something extraordinary. If you fill the universe with matter and energy and let the equations run forward, space-time does not stay still, it expands. Not might expand, not could expand if certain conditions are met. Expands, necessarily. According to the math, a static universe filled with matter is unstable. It will either expand or contract. It cannot simply sit there. Einstein himself initially found this so troubling that he added an extra term to his equations, a fudge factor called the cosmological constant, specifically to hold the universe still. He later called it his greatest blunder, because the universe does not hold still. It expands, and every observation we have made in the century since Einstein published his theory has confirmed that the expansion is real. Now comes the part that breaks most people's brains. When cosmologists say the universe is expanding, they do not mean galaxies are flying away from each other through space, like debris from an explosion scattering outward into an empty room. They mean space itself is growing. The distances between galaxies are increasing because new space is appearing in the gaps. The fabric of space-time is stretching. Not stretching into anything, just stretching, creating more of itself as it goes. You want to ask the question. Everyone does. If space is expanding, what is it expanding into? What is outside the universe? What is the space beyond space? The answer is that the question does not make sense. It assumes space is a thing embedded in a larger container. It assumes there is an outside. There is not. Space is not contained by anything. It is not sitting inside a bigger room. The universe is all the space there is. When space expands, it does not push outward into a pre-existing void. It generates new volume, more distance, more room from within itself. This is where the balloon analogy comes in. You've probably heard it before. Cosmologists use it constantly because it is one of the only ways to convey the basic idea without resorting to equations. But like every analogy, it is imperfect, and if you take it too literally, it will mislead you. So let me explain it carefully, and then let me tell you exactly where it breaks down. Imagine the surface of a balloon, not the interior, not the rubber itself, just the two-dimensional surface. Now imagine that surface is covered with dots. Each dot represents a galaxy. As you inflate the balloon, the surface stretches. The dots move farther apart. But here is the key point. None of the dots are moving through the surface. The surface itself is expanding. The distance between any two dots increases, not because the dots are travelling, but because the fabric they are embedded in is growing. Now imagine you are an ant living on that surface. You are two-dimensional. You cannot perceive up or down, only forward, backward, left, and right. From your perspective, the surface is the entire universe. And as the balloon inflates, you notice that every other ant, no matter which direction you look, is moving away from you. Not because you are at the centre. There is no centre on the surface of a sphere. Every point on the surface looks the same. Every ant sees the same thing. Everyone appears to be at the centre of an expansion, and yet no one actually is. That is the universe. We are the ants. The surface of the balloon is space-time, and the expansion we observe, galaxies receding in every direction, is not because we are special or centrally located. It is because space itself is stretching uniformly. Every observer, no matter where they are in the universe, sees distant galaxies moving away. The expansion looks the same from every vantage point. Now here is where the analogy breaks, and this is important. When you picture a balloon inflating, you automatically picture it sitting in a room. You picture the three-dimensional space around it, the air inside it, the person blowing it up. The balloon is expanding into that surrounding space, but the universe does not have that. The surface of the balloon in this analogy is not embedded in a higher dimensional space. It is all there is. There is no room around it. There is no outside. The expansion is intrinsic to the surface itself. The balloon metaphor works to illustrate uniform expansion and the absence of a center, but it fails the moment you start asking what the universe is expanding into. Because the answer is nothing. Not a void, not a vacuum, nothing. The question assumes a framework that does not exist. Space, in general relativity, is not a substance you can point to or bottle up. It is a set of relationships. A way of describing how far apart things are, how events are separated in time, how paths curve in the presence of mass. When we say space is expanding, we mean those relationships are changing. The distance between two galaxies that are not gravitationally bound to each other grows over time, not because the galaxies are moving, because the metric, the mathematical description of distances in space-time, is evolving. Think of it this way. If you draw a grid on a piece of paper and then stretch the paper, the grid lines spread apart. The distance between any 2 points on the grid increases, but the points themselves are not sliding across the paper. The paper is stretching, the grid is growing. That is what the expansion of the universe is doing. The grid is space-time, the points are galaxies. And the paper is not stretching into anything. It is just stretching. Now let me tell you what does not expand. Because this is where the next layer of confusion sets in. If space is expanding, why is your body not expanding? Why is the Earth not growing? Why is the solar system not stretching apart? The answer is that expansion only happens on the larger scales, where gravity and other forces are too weak to hold things together. You're held together by the electromagnetic force, which binds atoms into molecules and molecules into cells. The electromagnetic force is vastly stronger than the expansion of space at the scale of a human body. The Earth is held together by gravity, which is strong enough at planetary scales to resist expansion completely. The solar system is held together by the Sun's gravity, which dominates the local space-time enough that expansion does not even register. Even galaxies, despite being enormous, are gravitationally bound structures. The Milky Way is not expanding. Andromeda, our nearest large neighbour, is not expanding. The two galaxies are actually moving toward each other, pulled by mutual gravity, and will collide in a few billion years. Expansion only becomes significant in the vast stretches of space between galaxy clusters. In regions where gravity is too diffuse to pull things back together, that is where new space appears. That is where distances grow, and over billions of years that growth adds up. Clusters of galaxies that are not bound to each other drift farther apart. The voids between them grow larger. The universe becomes more spread out, more dilute as time goes on. But within each cluster, within each galaxy, within each star system, gravity dominates. Expansion loses. The local structure holds. This is not a trivial detail. It is one of the most important facts about the universe. Expansion is not a force. It does not push on things. It does not fight against gravity the way two opposing forces would. It is simply the default behavior of space-time in the absence of anything holding it together. If you have a region of space with no gravitational binding, no electromagnetic binding, no structure keeping things in place, that region will expand, distances will grow. And the farther apart two objects are, the faster the distance between them increases, because there is more expanding space in between. This is why distant galaxies appear to recede faster than nearby ones. It is not because they are moving faster, it is because there is more space between us and them, and all of that space is expanding. The farther away a galaxy is, the more expanding space lies along the line of sight, and the faster it appears to move away. This relationship, the connection between distance and recession speed, is called Hubble's law, named after Edwin Hubble, who first measured it in the 1920s, and it is one of the cleanest pieces of evidence we have that space itself is expanding. Hubble did not set out to discover the expansion of the universe. He was trying to measure the distances to galaxies and their velocities. He used a technique involving stars called Cepheid variables, which pulse at rates tied to their true brightness. Measure the pulse, calculate the brightness, compare it to how bright the star looks from Earth, and you get a distance. Once he had distances, he compared them to the velocities of the galaxies, which he measured by looking at how much their light had been redshifted. Light from objects moving away from us gets stretched to longer, redder wavelengths. The faster the object is receding, the more the light is stretched. What Hubble found was a clear relationship. The farther away a galaxy was, the faster it was receding. Double the distance, double the recession speed. Triple the distance, triple the speed. A perfect linear relationship. And that pattern only makes sense if space itself is expanding uniformly in all directions. If galaxies were just flying through static space, there would be no reason for distance and velocity to be related. Some galaxies would be moving fast, others slow, with no connection to how far away they are. But expansion explains it perfectly. More distance means more expanding space, which means a higher recession velocity. Now here is the truly strange part. Because space is what is expanding, objects can recede from us faster than the speed of light without violating relativity. Special relativity says nothing can move through space faster than light. That limit is absolute. But it does not say anything about how fast space itself can expand, and the equations of general relativity allow space to stretch as fast as it wants. In fact, at large enough distances, galaxies are receding from us faster than light. Not because they are moving through space that fast, but because the space between us and them is growing so rapidly that light leaving those galaxies right now will never reach us. We are already beyond each other's cosmic horizon. That sounds like science fiction. It is not. It is geometry. If space is expanding, and you are trying to send a beam of light from point A to point B, that light has to cross all the expanding space in between. And if space is expanding fast enough, the light never closes the gap. It is like trying to swim upstream in a river that is flowing faster than you can swim. You are moving forward through the water, but the water is carrying you backward faster than you can compensate. You never reach the shore. The light never reaches us. This is one of the reasons the observable universe is finite. Not because the universe itself is finite. We do not know if it is or not. But because there is a limit to how far we can see. Light from regions beyond a certain distance has not had time to reach us yet, and light from regions even farther away never will, because space is expanding too fast. The observable universe is the region of space from which light has had time to travel to us since the Big Bang. Beyond that is more universe, probably a lot more. We just cannot see it, and we never will. The edge of the observable universe is not a wall. It is not a boundary you could fly to and touch. It is simply the farthest distance from which light has reached us. And because the universe is expanding, that edge is also receding. Every second, light from slightly farther away enters the observable region. The horizon grows, but it does not grow fast enough to keep up with the expansion. Galaxies that are currently at the edge will eventually drift beyond it, and we will lose sight of them forever. Billions of years from now, an observer in the Milky Way will look out at the sky and see far fewer galaxies than we do today. Not because the galaxies disappeared, but because the space between us and them expanded to the point where their light can no longer reach us. Space is not empty. That is the lesson. Space is not nothing. It is a thing with properties, with behavior, with dynamics. It bends around massive objects. It ripples when those objects accelerate. It expands in the absence of forces that hold it together. And it does all of this without needing a container, without needing an outside, without needing anything beyond itself. This is a hard idea to accept because it runs so deeply against intuition. Our brains evolved to navigate a world of solid objects and fixed distances. A world where space is just the gap between things, passive and unchanging. We never encounter expanding space in everyday life. We never experience space-time curvature at a scale we can feel. And so when physicists tell us that space is a flexible, dynamic fabric, our first instinct is to reject it, to demand a better explanation, to insist that there must be something space is expanding into. There is not. The universe is not embedded in anything. It is not occupying a region of some higher dimensional void. It is not pushing outward into empty nothingness. It is simply becoming larger, more spacious. Creating room for itself by generating more of the fabric that constitutes distance and volume and the separation between events. The best way to picture this is not to imagine the universe as an object sitting in space, but to imagine space itself as the thing that is changing. Forget the balloon analogy for a moment. Forget the idea of a container. Just focus on the distances. The distance between galaxy A and galaxy B is increasing, not because A and B are moving, because the metric, the rule that tells you how to measure distance, is evolving. Yesterday, the distance was 1 billion light years. Today, it is 1,000,000,001. Tomorrow, it will be 1,000,000,002. The space between them is growing. New space is appearing in the gap. And that new space is not coming from somewhere else. It is not being imported from a reservoir of unused space sitting in another dimension. It is simply appearing. The fabric of space-time is stretching, and as it stretches, there is more of it. Einstein did not predict this lightly. He was initially horrified by the idea. A static universe made sense to him. An expanding one seemed chaotic, unstable, wrong. But the equations did not care what Einstein wanted. They predicted expansion whether he liked it or not. And when Hubble's observations confirmed that galaxies were indeed receding, Einstein had no choice but to accept it. The universe was not static. It was growing. And it had been growing since the beginning. That growth is not slowing down, by the way. For most of the 20th century, cosmologists assumed the expansion would eventually decelerate. Gravity, pulling everything back together, should slow the expansion over time. Maybe stop it. Maybe even reverse it, leading to a big crunch where the universe collapses back into a singularity. That was the expectation. In the late 1990s, astronomers measuring the distances and velocities of distant supernovae discovered the opposite. The expansion is accelerating. Galaxies are moving apart faster now than they were billions of years ago. Something is pushing space apart, and that something is not matter. It is not radiation. It is not anything we have ever directly detected. Physicists call it dark energy, and it makes up about 68% of the total energy content of the universe. We do not know what it is. We just know it is there, written into the fabric of spacetime itself, driving the expansion faster and faster as time goes on. If dark energy continues to dominate, and all evidence suggests it will, the universe will expand forever. Galaxy clusters will drift farther apart. The space between them will grow until no light from one can ever reach another. Each cluster will become an island, isolated in an ever-growing ocean of space. Stars will exhaust their fuel, black holes will evaporate, and eventually, trillions upon trillions of years from now, the universe will be cold, dark, and empty. A vast expanse of space with nothing in it but the faint whisper of radiation stretched to wavelengths longer than the observable universe itself. But that is a problem for the distant future. Right now, the expansion is shaping the cosmos we observe. It is carrying galaxies away from each other. It is stretching the light from distant stars into the infrared and radio bands. It is creating the large-scale structure of the universe, the vast web of galaxy clusters and filaments and voids that we see when we map the sky. And it is doing all of this not by pushing objects through space, but by changing the space itself, by making more room, by weaving new fabric into the cosmic tapestry with every passing second. The universe is not expanding into anything, it is expanding, full stop. And the mechanism behind that expansion, the way space stretches rather than objects moving, is the key to understanding what happens next. Because if space can stretch, it can also carry things along with it. It can sweep galaxies apart without those galaxies ever moving through their local space-time. And that difference, the difference between motion through space and the motion of space, is what the next part of the story is about. The Earth is moving. Right now, as you sit here trying to hold still, you're being carried along on a planet that spins at about 1,000 miles per hour at the equator. That spinning planet orbits the Sun at roughly 67,000 miles per hour. The Sun drags the entire solar system around the centre of the Milky Way at about 500,000 miles per hour. And the Milky Way itself is falling toward the Andromeda Galaxy at about 70 miles per second, pulled by mutual gravity across a gap of 2.5 million light-years. All of that is motion through space, objects moving along paths through a pre-existing framework. Planets orbit stars, stars orbit galactic cores. Galaxies fall toward each other or swing past each other, governed by gravity and momentum and the same rules that describe a baseball arcing through the air or a car turning a corner. This is the motion we understand. The motion our brains evolved to track. The motion that shows up in every physics textbook from high school onward. You have a thing. The thing has a velocity. The thing moves from point A to point B through the space in between. Straightforward, measurable, local. Now let me tell you about the other kind of motion. The kind that does not involve objects moving at all. There are galaxies so far away that their light has been travelling toward us for more than 13 billion years. We can see them in the deepest images taken by the James Webb Space Telescope, faint red smudges sitting at the edge of the observable universe. Those galaxies emitted their light when the universe was young, less than 1 billion years old. The light left, travelled through space at the maximum speed allowed by physics, and kept travelling for 13 billion years until it finally arrived at our telescopes. You would think, reasonably, that those galaxies are 13 billion light-years away. That is how far the light travelled. 13 billion years at the speed of light equals 13 billion light-years. Simple math. Except when astronomers calculate the actual distance to those galaxies today, accounting for the expansion of the universe, the answer is not 13 billion light-years. It is closer to 46 billion light-years, in some cases farther. The galaxies are not where the light says they should be. They have moved, or more accurately, space has moved them. Because while that light was travelling through the universe for 13 billion years, the universe was expanding. The space between us and those distant galaxies was stretching. And by the time the light reached us, the galaxies themselves were much, much farther away than they were when the light began its journey. This is not motion through space. The galaxies are not flying away from us at faster than light speed, punching through space-time like a ship going into hyperspace. They are sitting relatively still in their local region of space, drifting slowly through their local environment the way galaxies do. But the space between us and them is growing. New distance is appearing in the gap. The metric that describes how far apart 2 points are has changed. And that change, that stretching of the underlying fabric, is what we mean when we say the universe is expanding. The distinction matters. It is not semantic. It is not a technicality. It is the difference between two completely different physical processes. Motion through space and the expansion of space are not two descriptions of the same thing. They are separate phenomena, governed by different rules producing different effects. And if you do not understand the difference, you will spend the rest of your life confused about why the observable universe is 93 billion light-years across, when the universe is only 13.8 billion years old. So let's be very clear about what each one means. Motion through space is what happens when an object has a velocity relative to its surroundings. You throw a ball. The ball moves through the air. A comet flies past the sun. The comet moves through the solar system. A star is ejected from a galaxy by a close encounter with a black hole. The star moves through intergalactic space. In all these cases, the object is travelling from one location to another across a distance that already exists. The space is not changing. The object is. It goes from here to there. You can measure its speed. You can calculate how long the journey takes. You can, in principle, watch the object move. This kind of motion obeys special relativity. The speed limit is the speed of light. Nothing with mass can reach that speed, let alone exceed it. The faster an object moves through space, the more energy it takes to accelerate it further. As you approach light speed, your mass effectively increases, time dilates, lengths contract, and the universe does everything in its power to stop you from breaking the limit. This is not a suggestion. It is a law baked into the structure of space-time itself. If you are moving through space, you cannot go faster than light. Period. Motion through space dominates at local scales. Inside a galaxy, stars orbit the core. Planets orbit stars. Moons orbit planets. All of this is governed by gravity, momentum, and the rules of motion through a relatively static space-time. The distances between objects in a solar system are not growing because of cosmic expansion. They are fixed, or nearly so, held in place by the gravitational binding that keeps the system together. The Earth is not drifting away from the Sun because the universe is expanding. The Sun's gravity is far too strong. The metric expansion of space is happening, but at the scale of a solar system, it is so weak that gravity completely overwhelms it. The Earth stays in its orbit. The space between the Earth and the Sun is not stretching. Local structure wins. The same is true for galaxies. The Milky Way is not expanding. The stars inside it are not drifting apart because of cosmic expansion. They are gravitationally bound to the galaxy as a whole. The Andromeda Galaxy is not expanding either, and the fact that the two galaxies are moving toward each other, not away, is proof that local motion, driven by gravity, can completely override the expansion of space at these scales. Cosmic expansion only becomes significant when you look at distances between galaxies that are not gravitationally bound to each other. Between galaxy clusters separated by hundreds of millions of light-years, between superclusters separated by billions. That is where expansion takes over. That is where the stretching of space dominates. Now let's talk about what that stretching actually is. Because this is where most explanations fall apart. People hear the universe is expanding and they picture an explosion, a bomb going off, flinging debris outward into empty space, galaxies as shrapnel, flying away from a central point, scattering into the void. That image is wrong in almost every detail. The universe is not exploding outward from a center. There is no center. There is no void. And galaxies are not flying. The expansion of the universe is the increase in the distance between distant objects caused by the stretching of spacetime itself. Space is not a fixed grid. It is a flexible, dynamic thing. And under the right conditions, it grows. The distance between two galaxies that are far apart increases over time, not because the galaxies are moving through space, but because the space between them is literally getting bigger. More space is appearing in the gap. The fabric is stretching. The metric is evolving. This is not a metaphor. It is a description of what general relativity predicts and what observations confirm. The equations governing space-time allow it to expand uniformly in all directions, and when you measure the light from distant galaxies, you see exactly the pattern that expansion predicts. The farther away a galaxy is, the more its light has been redshifted, stretched to longer wavelengths. The stretching of the light is a direct consequence of the stretching of space. As the light travels through expanding space, the space itself pulls the wavelength longer. By the time the light reaches us, it has been shifted toward the red end of the spectrum, and the amount of redshift tells you how much space has expanded since the light was emitted. This is Hubble's law, the relationship between distance and redshift. The farther away a galaxy is, the faster it appears to be receding. But that recession is not motion through space. It is the cumulative effect of all the expanding space along the line of sight. Picture a photon leaving a distant galaxy and heading toward Earth. As it travels, the space it is moving through is stretching. Every meter of space the photon crosses is growing, becoming longer, and that growth adds up. By the time the photon arrives, the galaxy it left is much farther away than it was when the photon started. Not because the galaxy flew away, but because space grew in between. Here is the analogy everyone uses, and I am going to use it too because it actually works if you do not take it too far. Imagine a loaf of bread dough rising in an oven. The dough is full of raisins scattered throughout. As the dough rises, the raisins move farther apart. But the raisins are not walking through the dough. They are not propelling themselves outward. They are sitting still, embedded in the dough, and the dough itself is expanding. The farther apart two raisins are, the faster the distance between them grows, because there is more dough in between and all of that dough is rising. That is the universe. The dough is space. The raisins are galaxies. As space expands, galaxies move apart, not because they are travelling through space, but because the space between them is growing. And just like the raisins, every galaxy sees the same thing. From the perspective of any raisin, all the other raisins are moving away. There is no centre to the expansion. Every point in the dough looks like the centre. Every observer, no matter where they are, sees distant objects receding in all directions. Now here is where it gets strange, because if space itself is expanding, then there is no speed limit on that expansion. Special relativity says nothing can move through space faster than light, but it does not say anything about how fast space itself can stretch. General relativity allows spacetime to expand as fast as it wants, and at large enough distances it expands fast enough that galaxies are receding from us faster than the speed of light. This sounds impossible. It is not. The galaxies are not moving through space faster than light. They are sitting in space that is expanding. The space between us and them is growing so fast that the distance increases faster than light could cross it. A photon leaving one of those galaxies and heading toward us is moving through space at the speed of light as it must. But the space it is moving through is stretching, and if the stretching is fast enough, the photon never closes the gap. It is like running on a treadmill that is accelerating faster than you can keep up. You're running forward, but the ground beneath you is pulling you backward faster than you can compensate. You never reach the end. This is why the observable universe has a finite size even if the universe itself is infinite. There is a distance beyond which space is expanding so fast that light from those regions can never reach us. That distance defines the cosmic horizon, the edge of the observable universe, and that edge, today, sits about 46 billion light-years away in every direction. The total diameter of the observable universe is about 93 billion light-years. That number confuses people because the universe is only 13.8 billion years old. How can we see objects that are 46 billion light-years away if light has only been travelling for 13.8 billion years? The answer is expansion. The light did not travel 46 billion light years through static space. It travelled through expanding space. The galaxy that emitted the light was much closer when the light left. But while the light was travelling, space was stretching. The galaxy moved farther away. The space the light had already crossed stretched behind it. And by the time the light reached us, the galaxy was 46 billion light years away, even though the light had only been travelling for 13.8 billion years. This is not a trick, it is geometry. Trick. It is. The distance light travels through space, and the distance between 2 points in expanding space are not the same thing. One is a measure of how far the light has gone. The other is a measure of how far apart the objects are now, accounting for all the expansion that happened in between. And because space has been expanding the entire time, the current distance is much larger than the light travel distance. Here is another way to think about it. Imagine you are walking toward a destination 1 mile away. You walk at 3 miles per hour. In a static universe, it takes you 20 minutes to get there. But now imagine that while you are walking, the ground is stretching. Every meter you cross becomes 2 meters. By the time you reach the destination, the distance has grown to 2 miles. You walked for the same amount of time, covered the same amount of ground with your feet, but the destination is now farther away than it was when you started. That is what expanding space does to light. Now let's talk about why space is expanding in the first place, because this is not something Einstein predicted. It is something his equations allowed, reluctantly, and something observations forced cosmologists to accept. When Einstein first wrote down the field equations of general relativity, he assumed the universe was static, unchanging, the same size yesterday, today, and forever. But the equations did not agree. They predicted that a universe filled with matter would not stay still. It would either expand or contract. Gravity would pull it together or some repulsive force would push it apart. A static universe was unstable. Einstein did not like that. So he added a term to his equations, a constant he called the cosmological constant, specifically designed to counteract gravity and hold the universe still. It was a fudge, a patch, and Einstein knew it. He later called it his greatest blunder, because the universe is not static. It is expanding. And the observations that proved it came less than 15 years after he published his theory. In the 1920s, Edwin Hubble measured the distances to nearby galaxies and their velocities. He found that the farther away a galaxy was, the faster it was receding. A clear, linear relationship. Distance and velocity perfectly correlated. That pattern only makes sense if space itself is expanding. If galaxies were just flying through static space, there would be no reason for distance and speed to be related. Some would be moving fast, others slow, with no connection to how far away they are. But if space is expanding uniformly, then more distance means more expanding space, which means a higher recession velocity. The pattern Hubble found was a direct signature of cosmic expansion. For decades, cosmologists assumed the expansion was slowing down. Gravity, pulling everything back together, should decelerate the expansion over time, maybe stop it, maybe reverse it. The question was not whether the expansion was slowing, but how much. How long until gravity won? How long until the universe stopped growing and started collapsing back in on itself? Then in the late 1990s, 2 independent teams measured the distances and velocities of distant supernovae. Type 1a explosions that serve as cosmic mile markers. What they found shocked everyone. The expansion is not slowing down, it is speeding up. Distant galaxies are moving away faster now than they were billions of years ago. Something is pushing space apart, and that something is not matter. It is not radiation. It is not anything we have ever directly observed or isolated in a lab. Physicists call it dark energy, a name that means we do not know what it is. Dark because we cannot see it. Energy because it behaves like a kind of energy density built into the fabric of space itself. Every cubic meter of space, even the emptiest regions far from any galaxy, contains a tiny amount of dark energy. And that energy does not dilute as space expands. As the universe grows, new space appears, and that new space carries the same energy density as the old space. More space means more dark energy. More dark energy means a stronger push. The expansion accelerates. Dark energy makes up about 68% of the total energy content of the universe. Dark matter, the invisible stuff that holds galaxies together, makes up another 27%. Ordinary matter, the atoms that make up stars and planets and people, accounts for less than 5%. We are a rounding error in the cosmic budget. And the thing driving the expansion, the thing determining the future of everything, is a form of energy we do not understand and cannot directly detect. We only know it is there because of what it does. It stretches space, it accelerates expansion, and it is winning. This is not speculation. The measurements are solid. Multiple independent methods, using different techniques and different data sets, all converge on the same answer. The universe is expanding, and the expansion is accelerating. The galaxies we see today will drift farther apart over time. Galaxy clusters will become isolated islands separated by ever-growing voids. Light from distant galaxies will be stretched to longer and longer wavelengths until it fades into undetectability. Trillions of years from now, an observer in the Milky Way will look out at the sky and see almost nothing. A few nearby galaxies in the local group, gravitationally bound and immune to expansion. Everything else will have receded beyond the horizon, forever, but that is the distant future. Right now, the expansion is shaping the universe we observe. It is stretching the light from distant galaxies, creating the redshift pattern that let Hubble discover the expansion in the first place. It is growing the distances between galaxy clusters, carving out the voids and filaments that make up the large-scale structure of the cosmos. And it is defining the size of the observable universe, the region of space from which light has had time to reach us since the Big Bang. That region, today, extends about 46 billion light-years in every direction. The total diameter is 93 billion light-years. Those are the numbers you hear in documentaries and read in articles, and they are correct. But they are not the result of light travelling 93 billion light-years through static space. They are the result of light travelling 13.8 billion years through expanding space. The space the light crossed has been stretching the entire time. The galaxies that emitted the light were much closer when the light left. By the time the light reached us, those galaxies were 46 billion light-years away, and they are still moving farther. This is the paradox at the heart of cosmology. The universe is finite in age, but potentially infinite in size. The observable universe is a sphere centered on us, but there is no reason to think the universe stops at the edge of that sphere. There is more space beyond, probably a lot more. We just cannot see it because the light has not had time to reach us yet, and in many cases it never will. Space is expanding faster than light can cross it. The cosmic horizon is real. There are galaxies beyond it that we will never observe, not because they are too faint, but because the space between us and them is growing too fast for light to ever close the gap. The expansion of space is not something happening far away, in the distant reaches of the cosmos. It is happening everywhere, right now, in the room you're sitting in the space between your hand and the screen. The distances are so small, and the expansion rate is so slow that it does not matter. Gravity and electromagnetic forces hold everything together at these scales, completely overwhelming the expansion. But it is there. Space is stretching, the metric is evolving, the fabric of the universe is growing, and the difference between that growth and the motion of objects through space is the key to understanding everything that comes next. Because the observable universe has an edge, a boundary beyond which we cannot see. Not because there is nothing there, but because the light from anything beyond that boundary has not reached us yet, or cannot reach us, or will never reach us. The cosmic horizon is not a physical barrier. It is a limit imposed by the expansion of space itself. And understanding what that limit means, what it hides, and what it tells us about the universe beyond is where the next part of the story begins. There is a wall at the edge of everything you can ever know, not a physical wall, not a barrier made of matter or energy, a wall built from time and distance, and the stubborn fact that light, the fastest thing in the universe, has only been travelling for so long. Beyond that wall is more universe, almost certainly, probably an incomprehensible amount more, and you will never see it. Not because your telescopes are not powerful enough, not because your detectors are not sensitive enough, but because the light from those regions has not had time to reach you yet, and in many cases It never will. This is the cosmic horizon, the edge of the observable universe, and it is one of the most profound boundaries in all of physics. Not because it marks the end of space, but because it marks the end of information. The limit of what can ever be measured, tested, or confirmed. Everything beyond that boundary is speculation. Educated guesses built on patterns we observe within the boundary, extrapolated outward into a region we can never directly check, and depending on how the universe evolves, that boundary may be closing. Shutting more and more of reality away from view, with every passing billion years until future civilizations, if any exist, will look out at the night sky and see almost nothing. But let us start with what the horizon actually is, because the term gets thrown around in cosmology, and it does not mean what most people assume. When you hear horizon, you picture the line where the Earth meets the sky, the point where your view cuts off because the planet curves away beneath you. Climb higher and the horizon expands. Stand on a mountain and you can see farther. The horizon on Earth is a limit imposed by geometry and your position. It is not fundamental. It can be pushed back. The cosmic horizon is different. It is not imposed by where you are standing. It is imposed by when you are standing. By the age of the universe and the speed of light and the fact that information cannot travel faster than that speed. No matter how high you climb, no matter what instruments you build, the cosmic horizon does not move. It is a hard limit, a boundary defined not by your technology but by the structure of spacetime itself. The formal name for this boundary is the particle horizon. It marks the farthest distance from which light could have travelled to reach us since the Big Bang. If the universe is 13.8 billion years old, you might expect the particle horizon to sit 13.8 billion light years away. It does not. It sits about 46.5 billion light years away. The reason for that discrepancy is expansion. While light was travelling toward us, the space it had already crossed was stretching. The source of the light was moving farther away. By the time the light reached us, the object that emitted it was much farther than the light travel time would suggest. Picture a runner on a treadmill. The runner moves forward at a fixed speed, but the treadmill is also moving, pulling the starting line backward. If you measure how far the runner has travelled relative to the treadmill, you get one number. If you measure how far the starting line has moved away while the runner was running, you get a much larger number. The light travel distance is the first measurement. The current distance to the source is the second, and the difference between them is the expansion of space. The particle horizon today sits roughly 46.5 billion light years away in every direction. That makes the observable universe about 93 billion light years across. A sphere centered on Earth, or more accurately, centered on wherever you happen to be, because every observer in the universe has their own observable sphere. There is no universal center, no privileged location. Every point in space sees the same structure, a bubble of observability surrounded by regions that have not had time to send their light here yet. That bubble is not static. It is growing. Every second, light from slightly farther away enters the observable region. The horizon expands. New galaxies come into view. But the expansion of the horizon is not fast enough to keep up with the expansion of space. Galaxies that are currently near the edge of the observable universe are receding faster than the horizon is growing, which means they will eventually drift beyond it. Not because they are moving through space, but because the space between us and them is expanding so fast that their light will no longer be able to reach us. They will fade from view, redshifted into oblivion, and future observers will never know they existed. This is not speculation, it is math. The expansion rate of the universe, driven by dark energy, is accelerating. The farther away something is, the faster it recedes. At a certain distance, the recession speed exceeds the speed of light. Not because the galaxies are moving through space faster than light, which is impossible, but because the space between us and them is growing faster than light can cross it. And once an object crosses that threshold, its light cannot reach us. The photons it emits travel toward us at the speed of light, as they must. But the space they are crossing is stretching faster than they can traverse it. The gap never closes. The light never arrives. That threshold is called the Hubble sphere. It is the distance at which the recession speed of space equals the speed of light. Today, the Hubble sphere sits about 14.5 billion light years away. Objects beyond the Hubble sphere are receding faster than light, and yet, we can still see some of them. That sounds impossible. It is not. Because the Hubble sphere is not the same thing as the particle horizon. Here is why. Light emitted from a galaxy beyond the Hubble sphere starts out moving away from us, not because the galaxy intended to send its light away, but because the space between us and the galaxy is expanding so fast that even light moving toward us at the speed of light is being carried backward by the expansion. The photon is swimming upstream in a river that is flowing faster than it can swim. It loses ground. But here is the key. The expansion rate is not the same everywhere. As the photon travels, it crosses into regions where the expansion is slower, regions closer to us. Eventually it crosses back inside the Hubble sphere, into a region where space is expanding slower than the speed of light. At that point, the photon starts making progress. It begins closing the gap, and if it was emitted early enough, it eventually reaches us. This is why we can see galaxies that are today receding faster than light. The light we are seeing was emitted billions of years ago when those galaxies were closer and not yet beyond the Hubble sphere. The light has been travelling ever since, fighting against the expansion, crossing into slower regions and finally arriving here after a journey that took more than 13 billion years. By the time the light reached us, the galaxy had moved far beyond the Hubble sphere. It is now receding faster than light, and if we tried to send a signal back to that galaxy today, the signal would never arrive. Because the space between us and them is growing too fast, the message would never outrun the expansion. So the particle horizon, the edge of the observable universe, is not the same as the Hubble sphere. The particle horizon is farther. It includes galaxies that are currently receding faster than light because their light was emitted early enough to reach us. The Hubble sphere is a dividing line, a marker that tells you whether a signal sent today will ever arrive. Objects inside the Hubble sphere can still be reached. Objects outside cannot. But the distinction gets messier when you factor in dark energy. Because the expansion is accelerating, the Hubble sphere is not static. It is shrinking. Regions of space that were once inside the Hubble sphere are now outside it. Galaxies we can see today emitted their light when they were still reachable. By the time the light arrived, they had drifted beyond reach, and as the universe continues to expand, more and more galaxies will cross that line. The number of galaxies we can communicate with is decreasing. The number we can see is also decreasing, because galaxies near the edge of the observable universe are being redshifted into invisibility. Their light is being stretched to such long wavelengths that it becomes undetectable. This introduces a third kind of horizon, the event horizon. Not the event horizon of a black hole, though the concept is similar. The cosmic event horizon is the boundary beyond which events happening now will never be visible to us, no matter how long we wait. If a supernova explodes tomorrow in a galaxy beyond the cosmic event horizon, the light from that explosion will never reach Earth, not because the light is blocked, but because the space between us and the explosion is expanding too fast for the light to ever close the gap. The event horizon is currently about 16 billion light-years away, and it is shrinking. Galaxies that are just inside it today will drift outside tomorrow. Their future is being cut off from ours, permanently. This is the trajectory. The observable universe is a sphere of information that is growing in radius but shrinking in content. New light is reaching us every second, but it is ancient light from objects that are no longer where they appear to be. Meanwhile, the galaxies we see today are fading, drifting farther away, being redshifted into darkness. In a few 100 billion years, long after the Sun has died, long after the Milky Way has merged with Andromeda, an observer in whatever remains of our galactic neighbourhood will look out into space and see almost nothing. A handful of nearby galaxies, gravitationally bound and therefore immune to expansion. Everything else will have receded beyond the horizon. The cosmic microwave background, the faint afterglow of the Big Bang that currently fills the sky, will have been stretched to wavelengths so long that it will be undetectable. The evidence for the Big Bang will be gone. The evidence for expansion will be gone. Future cosmologists, if they exist, will look out at a nearly empty universe and have no way to deduce its history. They will be locked inside a bubble of a few galaxies surrounded by darkness, with no indication that anything exists beyond. The observable universe will have collapsed down to a single galaxy cluster, and the rest of reality will be hidden behind a horizon that can never be crossed. That future is unsettling, but what is more unsettling is what it tells us about now. Because if the horizon is closing, if information is being lost, then we're already living in a universe where most of reality is hidden from view. The observable universe is not the universe. It is a tiny bubble of space from which light has had time to reach us. Beyond that bubble is more space, more galaxies, more stars, more structure. We just cannot see it. How much more? Nobody knows. The observable universe contains roughly 2 trillion galaxies. Each galaxy contains billions to hundreds of billions of stars. That is a lot, but it is also a finite number, and finite does not mean complete. If the universe extends beyond the observable region, and there is no reason to think it does not, then the total number of galaxies is larger, possibly much larger, possibly infinite. This is where the speculation begins, because every measurement we can make, every observation we can confirm, is limited to the region inside the particle horizon. We can map the galaxies we see, we can measure the expansion rate, we can study the cosmic microwave background and use it to infer the conditions of the early universe. But all of that data comes from within the bubble. We have no direct information about what lies beyond. We can only extrapolate, assume the same laws of physics apply, assume the same large-scale structure continues, assume the universe does not suddenly change character the moment you cross the horizon. Those are reasonable assumptions. The universe, as far as we can tell, is homogeneous and isotropic at large scales. Homogeneous means it looks the same everywhere. Isotropic means it looks the same in every direction. If you zoom out far enough, the distribution of galaxies smooths out. There are no special regions, no preferred directions. Every large volume of space contains roughly the same number of galaxies, the same amount of matter, the same structure. If that pattern holds beyond the observable universe, and it probably does, then the universe beyond the horizon looks much like the universe within it. More galaxies, more clusters, more voids, stretching out in all directions, possibly forever, but we cannot prove that. We can only assume it based on the data we have, and assumptions, no matter how reasonable, are not the same as observations. The edge of the observable universe is the edge of confirmed reality. Beyond that line is inference, a best guess about what exists built on patterns we see inside the bubble and extended outward into territory we can never check. This is a strange position for science to be in. Science relies on observation, on measurement, on the ability to test predictions and confirm or reject hypotheses. But the regions beyond the cosmic horizon are by definition unobservable. You cannot point a telescope at them, you cannot send a probe, you cannot collect data. The information has not reached you and in many cases never will. So what do? How do you build a theory of the universe when most of the universe is hidden from you? The answer is that you do the best you can. You use the data you have. You look for patterns, you build models that explain what you see and predict what you cannot. And you accept that some questions may never have answers, at least not answers you can confirm. This does not mean cosmology is guessing. The observable universe is real, the measurements are solid, the expansion is confirmed. The age of the universe, the density of matter, the temperature of the cosmic microwave background, all of it has been measured to high precision. The models we build are constrained by that data. They have to fit what we see. And the fact that they do fit, that the same laws of physics explain everything from the formation of the first atoms to the structure of galaxy clusters today, gives us confidence that those laws apply beyond the horizon as well. But confidence is not certainty, and the cosmic horizon is a reminder that there are limits to what we can know. Not practical limits that better technology might overcome, but fundamental limits imposed by the structure of spacetime itself. The speed of light is finite. The age of the universe is finite. The combination of those two facts creates a boundary, and that boundary is absolute. Here is the truly strange part. The boundary is not the same for everyone. Every observer in the universe has their own particle horizon, their own observable sphere. If you could somehow travel to a galaxy 10 billion light-years away, you would see a completely different set of galaxies at the edge of your new observable universe. Some of the galaxies you see from Earth would be invisible from there, because their light would not have had time to reach that location, and new galaxies, invisible from Earth, would come into view. The observable universe is not a fixed region. It is observer-dependent, a bubble that moves with you, centered on wherever you happen to be. That means the universe contains overlapping bubbles of observability. Each observer sees their own sphere. Some of those spheres overlap, some do not. Two observers on opposite sides of the universe, separated by more than the diameter of the observable universe, would have no galaxies in common. Their observable regions would not intersect. They would be looking at completely different parts of the cosmos, and neither would have any way to confirm that the other existed. They would be causally disconnected, unable to communicate, unable to observe each other. Living in the same universe but forever separated by the expansion of space. This is not science fiction, it is geometry, a direct consequence of the finite speed of light and the expansion of space. The universe is bigger than any single observer can see, and if it is infinite, which it might be, then every observable universe is an infinitesimal fraction of the whole. A vanishingly small patch of a cosmos that extends without bound in all directions, filled with galaxies and stars and planets that no one will ever observe. That possibility is unsettling for a reason that has nothing to do with technology or measurement. It is unsettling because it means reality is bigger than knowledge. There are facts about the universe, true statements about what exists and where and how that no one can ever confirm, not because the facts are hidden in some temporary way, but because they are fundamentally inaccessible. The light has not arrived, the signal cannot be sent, the information is lost behind a horizon that cannot be crossed. Philosophers have a term for this, they call it epistemic humility. The recognition that there are limits to what can be known. Not limits imposed by ignorance or lack of effort, but limits imposed by the structure of reality itself. You can build the perfect telescope, design the perfect detector, and still run into the wall. The wall is not technological, it is cosmic, and it is absolute. This has implications. If the observable universe is only a fraction of the total universe, then every statement about the universe as a whole is necessarily incomplete. We can say the observable universe is flat, we can measure its density, we can map its large-scale structure, but we cannot say with certainty that the entire universe is flat, or that it has the same density everywhere, or that the structure we see extends indefinitely. We can only say that within the region we can observe, these things are true. Beyond that, we are guessing. Most cosmologists believe the universe extends beyond the observable region. The assumption is built into the standard model. Inflation predicts it. If the universe underwent a period of exponential expansion in its first fraction of a second, as the evidence strongly suggests, then the total universe is vastly larger than the observable part. Inflation stretched space so much that regions which were once close enough to communicate are now separated by distances light could never hope to cross. The observable universe in that picture is a tiny bubble inside a much larger expanse, and that expanse may be infinite, or it may not. The universe could be finite, curved back on itself in a way that makes it closed but unbounded, like the surface of a sphere. Walk in any direction on a sphere and you never hit an edge. You just loop back around, a finite universe with no boundary. That is allowed by the equations. It fits some of the data. But it is not required. The measurements we have are consistent with a flat universe, and a flat universe, if it is flat everywhere, is infinite. So which is it? Finite or infinite? Bounded or unbounded? We do not know. The curvature of space is so close to zero that current measurements cannot distinguish between a perfectly flat universe and a very slightly curved one. If the universe is closed, the curvature is so gentle that it only becomes noticeable at scales much larger than the observable universe. We would need to see beyond the horizon to measure it, and we cannot. This is the paradox of the cosmic horizon. It defines the edge of what we can observe, but it also defines the edge of what we can ever confirm. The universe beyond the horizon is real, probably, but it is also unknowable. It exists, but it does not exist for us in any measurable sense. We are trapped inside a bubble of information, surrounded by a vast and possibly infinite expanse that we can theorize about but never directly probe. And that bubble is shrinking, not in radius, but in content. As the universe expands, galaxies drift farther apart. The space between them grows, and eventually, one by one, they fade from view. The light they emit is stretched to undetectable wavelengths. The galaxies themselves recede beyond the event horizon. The future we share with them is severed. They move into a region of spacetime from which no signal, no light, no information of any kind will ever reach us again. In a few 100 billion years, an observer in the Milky Way, assuming anything resembling an observer still exists, will look out into the cosmos and see a handful of galaxies, the local group, gravitationally bound, immune to expansion. Everything else will be gone, not destroyed, just hidden. Pushed beyond the horizon by the relentless stretching of space. The cosmic microwave background will be gone. The evidence for the Big Bang will be gone. The expansion itself will be undetectable, because there will be nothing left to measure it against. Future cosmologists will have no way to deduce the history of the universe. They will be stuck in a dark, nearly empty cosmos, with no indication that anything ever existed beyond their tiny corner of space. We are lucky. We live in an era when the universe is still young enough, still dense enough, that we can see the evidence. We can measure the expansion. We can detect the cosmic microwave background. We can map the large-scale structure of the cosmos and trace its history back to the Big Bang. But that window is closing. The information is fading, and once it is gone forever. The cosmic horizon is not just the edge of space, it is the edge of time, the edge of history, the boundary beyond which the past itself becomes inaccessible. And if that boundary is real, if the horizon is closing and the universe is hiding itself away piece by piece, then what does that say about the universe beyond? The regions we cannot see, the galaxies we will never observe, the structures that exist but remain forever out of reach. Are they bound by the same horizon? Do they see us fading from their view, drifting beyond their own cosmic edge, disappearing into a darkness from which no signal can return? Are we already ghosts to them, visible only in the ancient light we emitted billions of years ago, while our present selves have moved beyond the threshold where communication is possible? That question has no answer. Not because the answer is unknown, but because the question cannot be tested. The regions beyond the horizon are, by definition, beyond reach. They are part of the universe, but they are not part of our universe in any operational sense. They exist in a realm of permanent inaccessibility, where facts are true but unverifiable, where events happen but leave no trace we can ever detect. This is the edge of knowledge. Not the edge of space, the edge of information, the boundary where observation stops and speculation begins. And beyond that boundary lies a universe we can imagine but never confirm, a cosmos that may be infinite, filled with an endless sea of galaxies and stars, or finite, wrapped back on itself in dimensions we cannot perceive. A reality that is real but unknowable, existing in parallel to the small bubble of space we call the observable universe, forever separated by a wall built from time and distance and the speed of light. The cosmic horizon is not a wall you can break through with a bigger telescope. It is not a technical problem waiting for a better detector. It is a boundary imposed by physics itself, a line drawn by the finite speed of light and the finite age of the universe. Beyond that line is more universe, almost certainly, but you will never see it. The light has not had time to reach you. And in many cases, because space is expanding faster than light can cross it, the light never will. That should bother you, because it means most of reality is hidden. The observable universe, that sphere of space roughly 93 billion light-years across, is not the universe. It is a bubble. It is a tiny region from which information has managed to reach Earth in the 13.8 billion years since the Big Bang. Everything outside that bubble is real. It exists. Stars are forming there. Galaxies are colliding there. Planets are orbiting suns you will never see. And none of it can ever send a signal back to confirm its existence. So the question becomes unavoidable. If the observable universe is only a piece of the total universe, how much more is there? Is the universe just slightly larger than what we can see? A finite expanse that happens to extend a bit beyond our horizon? Or is it vastly larger, incomprehensibly larger, infinite? This is not idle speculation. This is a direct consequence of the most successful theory we have about the early universe: inflation. The hypothesis that space underwent a period of exponential expansion in the first fraction of a second after the Big Bang. Inflation solves real problems. It explains why the cosmic microwave background has the same temperature in every direction. It explains why space appears flat. It predicts the pattern of tiny density fluctuations we observe in the early universe, fluctuations that eventually grew into galaxies. Inflation works. The predictions match the data. And one of the things inflation predicts, almost as a side effect, is that the total universe is much, much larger than the part we can see. Here is why. Inflation did not happen everywhere at once and then stop everywhere at once. It happened in patches. Imagine a pot of water starting to boil. Bubbles form in different places at different times. Some bubbles grow. Some merge. The boiling process is not uniform. It is chaotic. Inflation, according to the equations, behaves the same way. In some regions of space, the inflaton field, the hypothetical field driving inflation, rolled down its energy hill and inflation ended. That is where normal expansion took over. That is where the hot Big Bang began. That is where galaxies eventually formed. Our observable universe is one of those regions, a bubble where inflation stopped and structure began to grow. But in other regions, the inflaton field did not roll down the hill. It stayed at the top, and in those regions, inflation kept going. Space kept doubling, kept expanding, faster and faster. Those regions inflated so much that they are now impossibly far away, separated from us by distances light could never hope to cross even if it travelled forever. And within those regions, new bubbles formed. New patches where inflation ended and new Big Bangs began. And within those bubbles, the process repeated, over and over. An endless fractal of expanding space, with pockets of slower expansion scattered throughout. This is called eternal inflation. And the word eternal is not poetic. It is literal. Once inflation starts, it never fully stops. It ends locally, in patches, but globally it continues forever. New regions keep inflating. New bubbles keep forming. The process has no off switch. It runs on its own, fed by the quantum fluctuations inherent to the inflaton field. Every time a region tries to settle down, a quantum fluctuation somewhere else kicks it back into inflation mode. Space keeps growing. Universes keep forming, and the structure that results is not a single cosmos, it is a multiverse. An infinite collection of bubble universes, each one causally disconnected from the others, each one with its own Big Bang, its own history, its own galaxies and stars. Our observable universe is one bubble, one patch of space where inflation ended roughly 13.8 billion years ago. The cosmic microwave background we see, the afterglow of our Big Bang, is the light from the moment our patch transitioned from inflation to normal expansion. But that transition did not happen everywhere. It only happened here, in our bubble. Other bubbles had their own transitions at different times under different conditions. And the space between bubbles is still inflating, stretching so fast that no signal from one bubble can ever reach another. This is not science fiction. This is what the equations of inflation predict when you run them forward. The theory that explains the cosmic microwave background, the theory that solves the horizon problem and the flatness problem, naturally produces eternal inflation as a consequence. You do not have to add anything extra. You do not have to modify the theory. Eternal inflation falls out of the math. And if eternal inflation is real, the multiverse is real. Not as a speculative add-on, as an unavoidable prediction. That makes cosmologists uncomfortable, because the multiverse by definition is unobservable. The other bubbles are beyond our cosmic horizon, not just beyond the current horizon. Beyond any horizon we could ever reach. The space between bubbles is inflating faster than light. You cannot send a probe there, you cannot point a telescope at them, you cannot gather data. Every other universe in the multiverse is in principle forever inaccessible, which means the multiverse is not a testable prediction. It is a consequence of a testable theory, and that distinction matters. Science works by making predictions and checking them. You propose a hypothesis, you design an experiment, you collect data, you confirm or reject the hypothesis. That process has limits. Some predictions are hard to test, some require technology we do not have yet. But the multiverse is different. It is not hard to test, it is impossible to test. Not because we lack the tools, because the things we are trying to observe are causally disconnected from us. They exist, if they exist, in regions of spacetime from which no information can ever reach us. You cannot confirm what you cannot see, and you cannot see what is hidden behind a horizon that cannot be crossed. So why do cosmologists take the multiverse seriously? Because the alternative is worse. If you want to avoid the multiverse, you have to modify inflation. You have to add a mechanism that shuts inflation off everywhere at once. You have to fine-tune the theory so that inflation ends globally, not locally, producing a single universe instead of a cascade of bubbles. That is possible. You can write down models that do it. But those models are more complicated. They require extra assumptions. They feel contrived, and they do not explain the data any better than the simpler models that produce eternal inflation naturally. Occam's razor favours the multiverse, not because the multiverse is simple, it is not, but because the theory that predicts it is simple. Inflation, in its most straightforward form, produces eternal inflation. If you accept inflation, which the data strongly supports, you get the multiverse for free. You do not have to believe in it, you do not have to like it, but you do have to explain why the equations are wrong if you want to avoid it, and the equations are not obviously wrong. They fit the observations, they make predictions that match the cosmic microwave background. They explain the large-scale structure of the universe. They work. So the multiverse sits in this strange limbo, a prediction of a successful theory that cannot itself be tested, a consequence that follows logically from premises we have confirmed, but describes a reality we can never observe. Now let's talk about what the multiverse might actually look like, because eternal inflation is not the only game in town. There are other ideas, other ways the universe, or universes, could be structured, and some of them are even stranger than eternal inflation. One of the most talked about alternatives is brain cosmology. The word brain is short for membrane, and the idea comes from string theory. String theory, which is still unproven but mathematically elegant, suggests that the fundamental building blocks of reality are not particles, but tiny vibrating strings, and those strings exist in more than the 3 dimensions of space we experience. They exist in 10 or 11 dimensions. Most of those extra dimensions are curled up so small we cannot see them. But some versions of the theory allow for large extra dimensions, dimensions big enough to contain entire universes. In this picture, our universe is not a bubble of space floating in a void. It is a 3-dimensional membrane, a brain, embedded in a higher dimensional space called the bulk. Think of it like a sheet of paper floating in a room. The paper is 2-dimensional, the room is 3-dimensional. Anything confined to the surface of the paper can only move forward, backward, left, or right. It cannot perceive up or down. It has no access to the 3rd dimension. We are like that. We live on a 3-dimensional brain, moving through time, unaware of the higher dimensions around us. Everything we see, every particle, every force except gravity, is stuck to the brain. But gravity is different. Gravity can leak into the bulk. That is why it is so much weaker than the other forces. It is not fully confined to our brain. It spreads out into dimensions we cannot see. If our universe is a brain, there could be other brains, other 3-dimensional membranes floating through the higher dimensional bulk. Each one could contain its own universe, its own matter, its own forces. And those universes would be invisible to us because the particles and light in one brain cannot cross into another. The only thing that connects them is gravity, leaking through the bulk too weak to notice at the scales we can measure. This is not just abstract math. Brain cosmology makes testable predictions, or at least it tries to. If brains exist, they can move, they can drift through the bulk. And if 2 brains collide, the energy of the collision could trigger a big bang. Not the Big Bang, a big bang, one of many. Every collision produces a new burst of energy, a new expansion, a new universe, and the process could repeat indefinitely. Brains collide, bounce apart, drift, collide again. Each collision creates a new cosmos. Each cosmos evolves, forms galaxies, maybe even life, and eventually cools and fades. Then the brains collide again and the cycle starts over. This is called the ekpyrotic universe model. The name comes from the ancient Greek word for conflagration, a cycle of creation and destruction, an eternal process with no beginning and no end. Just an endless series of big bangs, each one erasing the evidence of the one before, each one producing a new universe that lives and dies and is replaced by the next. The idea is beautiful. It solves the problem of what came before the Big Bang by saying there was no before. There was a previous cycle, a previous universe that collapsed or faded, followed by a collision that triggered our Big Bang. And when our universe runs its course, another collision will trigger the next one. The multiverse in this picture is not a collection of simultaneous bubbles. It is a sequence of universes, one after another, strung along a timeline that has no start and no finish. But like eternal inflation, brain cosmology has a problem. The extra dimensions have never been observed. String theory, the framework that predicts them, has never been tested. The ekpyrotic model makes some predictions about the cosmic microwave background, patterns that would distinguish it from standard inflation. But so far the data does not clearly favour one model over the other. Brain cosmology is elegant. It is mathematically consistent, but it is not confirmed. And until we find evidence of extra dimensions, or detect a signature of a brain collision, it remains a hypothesis, a possibility, not a fact. So we have two pictures: eternal inflation, which produces an infinite collection of bubble universes separated by inflating space, and brain cosmology, which produces a sequence of universes born from collisions in higher dimensions. Both predict a multiverse. Both are grounded in serious physics. Both are consistent with the data we have, and both are completely untestable in their multiverse aspects. There is a third option, one that does not require inflation or extra dimensions, one that follows directly from quantum mechanics. It is called the many worlds interpretation, and it says that every quantum measurement splits the universe into multiple branches. Every time a particle could go left or right, the universe divides. One branch where it went left, one branch where it went right. Both branches are real. Both continue evolving, and over time the number of branches grows exponentially. Trillions upon trillions of parallel universes, each one representing a different outcome of every quantum event that has ever happened. This sounds insane. It is also the most straightforward interpretation of quantum mechanics. Quantum mechanics describes particles in terms of probabilities. Before you measure a particle's position, it does not have a definite position. It exists in a superposition, a combination of all possible positions at once. When you measure it, the superposition collapses and you get a single outcome, one position, one result. But the equations do not tell you why the collapse happens. They do not explain how a particle decides which outcome to choose. The collapse is added to the theory by hand. It is called the measurement problem, and it has been bothering physicists since the 1920s. The many worlds interpretation solves the measurement problem by getting rid of the collapse. It says the particle does not choose. All outcomes happen, the universe splits into branches, one for each possible result, and you, the observer, split along with it. In one branch, you measure the particle on the left. In another branch, you measure it on the right. Both versions of you are real. Both think they are the only one, and both continue living in their separate branches, unaware of the other. This interpretation has no extra assumptions. It just takes the equations of quantum mechanics literally. No collapse, no hidden variables, just the wave function, evolving smoothly, branching into an ever-growing tree of parallel realities. It is simple, it is consistent, and it predicts a multiverse as a direct consequence of quantum mechanics. But here is the problem. The branches never communicate. Once the universe splits, the two branches are separate. They evolve independently. You cannot send a signal from one branch to another. You cannot detect the other branches. You cannot confirm that they exist. The many worlds interpretation makes the same experimental predictions as standard quantum mechanics. Every measurement you perform, every experiment you run, gives the same probabilities whether you believe in many worlds or not. The only difference is the interpretation, what you think is happening behind the scenes. And interpretations are not testable, they are philosophical choices. So the many worlds multiverse, like the eternal inflation multiverse and the brain cosmology multiverse, is unobservable. It exists, if it exists, in a realm we can never access. A consequence of a theory that works, describing a reality we can never probe. You see the pattern. Every multiverse scenario has the same structure. A well-motivated theory grounded in real physics that predicts the existence of regions or branches or universes we cannot observe. The predictions are logical, the theories are not arbitrary, but the multiverse itself is hidden, forever, by definition. This raises a serious question. If you cannot test it, is it science? If a theory predicts something unobservable, does that prediction count as a scientific statement or a philosophical one? Physicists argue about this constantly. Some say the multiverse is a legitimate consequence of testable theories and should be taken seriously. Others say that if you cannot observe it, even in principle, it is not science. It is metaphysics dressed up in equations. The debate is not settled. But here is what most cosmologists agree on. Inflation is real. The evidence is strong. The predictions match the data. And if inflation is real, eternal inflation probably follows. You can try to avoid it by modifying the theory, but those modifications feel forced. The simplest models produce a multiverse naturally. So the multiverse is not something we invented because it sounded cool. It is something we stumbled into because the equations led us there. Does that mean it is real? Maybe. Probably. We do not know. The multiverse is the most well-motivated idea in cosmology that cannot be tested. A prediction that follows logically from premises we trust, describing a reality we can never confirm. It sits at the boundary between science and philosophy, in a space where evidence runs out and inference takes over. And that brings us to the measure problem. Because even if the multiverse is real, even if eternal inflation produces an infinite number of bubble universes, we still have a problem. How do you calculate probabilities in an infinite multiverse? If every possible outcome happens somewhere infinitely many times, how do you decide which outcomes are typical and which are rare? In a single universe, probabilities are straightforward. You count the number of ways something can happen, divide by the total number of possible outcomes, and you get a probability. But in an infinite multiverse, the total number of outcomes is infinite. Every event that can happen does happen, infinitely many times. So how do you compare them? How do you say one thing is more likely than another when both happen infinitely often? This is called the measure problem, and it is one of the deepest unsolved issues in cosmology. Without a solution, eternal inflation cannot make unique predictions. You can adjust the measure, the way you count outcomes, and get different answers. Some measures predict a universe like ours is typical, others predict it is rare. There is no consensus on which measure is correct, and without that consensus, eternal inflation loses its predictive power. It becomes a framework that can explain anything, which means it explains nothing. Cosmologists are working on this. Some suggest using the observable universe as a reference frame, only count outcomes that occur within a single observer's pass-light cone. That gives you a finite region to work with and avoids the infinities. Others propose different cutoffs, different ways to regulate the infinite multiverse and extract finite testable predictions. None of the proposals are fully satisfying yet. The measure problem is still open. But here is the key point. The measure problem is a technical issue. It does not invalidate the multiverse. It just means we have not figured out how to use the multiverse to make precise predictions yet. The multiverse is a consequence of inflation. Inflation is a consequence of the data. So the multiverse is not going away just because the measure problem is hard. Now let's connect this back to the paradox we started with. The universe expanded into nothing. That statement, which sounds impossible, makes sense once you understand that space itself is expanding. Space is not a container, it is a thing, a fabric that can stretch and grow. The Big Bang was not an explosion into space, it was the beginning of space. The initial expansion created the room for everything else to exist, and that expansion is still happening. Right now, space is still stretching, distances are still growing, new space is still appearing in the gaps between galaxies. If inflation is correct, that process did not happen once, it has been happening forever. In some regions, space is still inflating exponentially, creating vast stretches of new space every fraction of a second. In other regions, inflation ended, and normal expansion took over. Our universe is one of those regions, a bubble where inflation stopped and the hot Big Bang began. But the process that created our bubble is still running elsewhere, still producing new bubbles, new universes, each one expanding into nothing, because nothing is what expansion creates. Not a void that was already there, just more space, more room, more fabric woven into the structure of reality. This is what the multiverse means. Not a collection of universes floating in some pre-existing superspace, but a network of expanding regions, causally disconnected, each one creating its own space as it grows. Each one with its own cosmic horizon, each one isolated from the others by the same mechanism that isolates distant galaxies from us. The expansion of space, the stretching of the metric, the relentless growth of distance that eventually outpaces the speed of light and severs all communication. The multiverse, if it exists, is not somewhere else. It is everywhere. Overlapping with our space at the larger scales, separated from us by inflating regions we can never observe. Connected only by the shared history of a process that began before our Big Bang and may never end. Every bubble is an island. Every universe is alone. And the space between them is growing faster every moment, pushing them farther apart, ensuring that no signal, no light, no information will ever cross from one to another. That is the multiverse. Not a fantasy, not a metaphor. A consequence of taking seriously the idea that space is a thing that can stretch. If space can stretch, it can stretch forever. If it can stretch forever, it can create regions that never stop stretching. And if those regions exist, new universes form inside them, endlessly, eternally, with no way to confirm or deny any of it, because the evidence is hidden behind a horizon we can never cross. So the universe did not expand into anything, it expanded. And if eternal inflation is correct, it is still expanding. Not just here, everywhere. In ways we cannot see and never will. Creating space, creating universes, creating an infinite cascade of realities, each one as real as ours, each one as isolated, each one expanding into nothing because nothing is all there is. Space creates itself. The universe makes room for itself. And the multiverse, if it is real, is the inevitable result of a process that started small and has no mechanism to stop. This is where the paradox loops back on itself. You asked what the universe expanded into. The answer is nothing. You asked how space can grow without a container. The answer is that space does not need one. You asked whether the universe is all there is. And the answer, if the equations are right, is no. The universe is one bubble in an ocean of bubbles, each one forever beyond reach, each one asking the same questions, each one expanding into the same nothing, alone. You have spent the last 6 chapters learning why your brain is not equipped for this question. You have walked through the birth of spacetime, the stretching of the cosmic fabric, the expansion that carries galaxies apart without moving them through anything, the horizon that seals most of reality away from view, and the possibility that our universe is one bubble in an infinite froth of universes, each one expanding into nothing because nothing is what expansion makes. And now, after all of that, after every explanation and analogy and attempt to make the impossible feel slightly less impossible, we come back to where we started, the paradox, the question that refuses to behave, the thing that sounds like nonsense no matter how carefully you phrase it. What did the universe expand into? You know the answer now. You have heard it multiple times. The universe did not expand into anything. Space itself expanded. There was no container, no void, no outside. The Big Bang was not an explosion in space. It was the beginning of space. Expansion is not motion through a pre-existing framework. It is the creation of distance itself. The universe makes room for itself by generating more of the fabric that constitutes room. It does not need permission. It does not need a place to go. It simply grows. That answer is correct. It is supported by every piece of evidence we have. It follows directly from general relativity, the most thoroughly tested theory of gravity ever devised. It matches the observations. It explains the data. And it is still utterly unsatisfying. Because your brain, which evolved to navigate a world of solid objects and fixed distances, keeps trying to picture the expansion as something moving into something else, you cannot help it. The moment you imagine space growing, you imagine it growing into a region that was already there, an empty room that space is filling up, a void that space is displacing. Your intuition will not let go of the idea that expansion requires a place to expand into. Even after everything you have learned, even after understanding that space is not a container but a thing, the paradox lingers, stubborn, unresolved. So let me say it differently. Let me reframe the entire question in a way that might finally make the paradox collapse under its own weight. The universe is not expanding into anything because the universe is the definition of anything. It is not occupying space. It is space. It is not moving through time. It is time. The fabric of space-time is not embedded in a larger structure. It is the structure, all of it, the totality, the only framework that exists. And when that framework grows, it does not grow into something else. It grows into more of itself. Space creates space. Distance generates distance. The universe expands by becoming larger, not by filling a container that was sitting there waiting. This is not wordplay. This is the most accurate description we have of what expansion actually is. The universe is a self-contained, self-creating system, It does not require an outside because outside is a concept that only makes sense within the universe. You can talk about the outside of a balloon because the balloon exists in a room. You can talk about the outside of a building because the building exists on a planet. But the universe does not exist in anything. It is the thing that provides the context for existence. There is no metaspace surrounding it. No higher level container holding it in place. The universe is all the space there is. And space, according to the equations of general relativity, can expand. Not by pushing into a void, by generating new volume, by stretching the metric that defines distance, by creating more of itself, continuously, without reference to anything external. This is what makes the paradox so slippery. The question itself assumes a framework that does not apply. When you ask what the universe expanded into, you're assuming there is a distinction between the universe and the space it occupies. You are treating space as a container and the universe as the contents. But that distinction does not exist. The universe is not in space, it is space. The two are the same thing, and when space expands, it does not move into a region that was already spatial. It makes that region spatial. It creates the distance, it defines the separation. Before the expansion, the distance did not exist. After the expansion, it does. That is what expansion means. The generation of new distance where there was no distance before. Now let us go back to the beginning. Not the beginning of the universe. The beginning of the question. The reason you are confused in the first place. You have been told, probably since childhood, that the universe began with the Big Bang. A moment 13.8 billion years ago when everything started. Time, space, matter, energy, all of it. Before that moment, there was nothing. And from that nothing, the universe appeared. Exploded into being. Expanded outward from a single point until it became the vast cosmos we see today. That story is mostly wrong. Not in its conclusion. The universe did begin roughly 13.8 billion years ago. The evidence for that is overwhelming, but in its framing, the picture it creates in your head. Because when you hear that story, you imagine a point sitting in darkness, a tiny seed of energy waiting to ignite, and then boom, expansion. The seed explodes, matter flies outward, and the universe grows like a fireball spreading through empty space. That image is burned into popular culture. It shows up in documentaries, textbooks, museum exhibits. It is how everyone pictures the Big Bang, and it is completely, fundamentally misleading. The Big Bang was not an explosion at a point in space. It was the beginning of space itself. There was no darkness surrounding the initial state because darkness is a thing that exists in space. There was no emptiness waiting to be filled because emptiness is a spatial concept. There was no point from which the expansion originated because a point is a location, and location is something space provides. Before the Big Bang, there was no space, no time, no stage, no container, no framework. The universe did not appear inside something. It appeared as something. Space and time came into existence together, and everything that followed, the cooling, the formation of particles, the ignition of stars, was a process happening within that expanding framework, not a process spreading into a pre-existing void. This is where the phrase into nothing starts to make sense. Not because there was a nothing that the universe expanded into, but because the question of what came before, or what surrounds the universe, or what it is expanding into assumes the existence of spatial and temporal concepts that do not apply. Before the Big Bang, there was no before. Not a moment of time sitting 1 second earlier, not a blank stretch of duration waiting for something to happen. The timeline itself began with the Big Bang. There is no prior moment to point to. The question what happened before the Big Bang is grammatically correct but logically meaningless. It is like asking what is north of the North Pole. The words make sense individually, but the sentence does not describe anything real. Because north stops being a direction once you reach the pole. You cannot go farther north. The concept breaks down. The same thing happens when you try to go before the beginning of time. There is no before. The concept has nowhere to attach. And the same logic applies to space. If the Big Bang marks the beginning of space, then asking what the universe expanded into is like asking what is outside of all space. The question assumes there is a spatial region beyond the universe, a place where space is not. But that assumption is incoherent. Space is not a substance that fills a region. It is the region. It is the framework that defines what a region even is. Outside of space does not mean anything. It is not a location you could travel to. It is not a void sitting beyond the edge. It is a non-concept, a phrase that sounds like it should refer to something, but actually refers to nothing at all. This is what cosmologists mean when they say the universe is not expanding into anything. They do not mean it is expanding into a void. They mean the question is based on a misunderstanding of what expansion is. Expansion is not motion. It is not the universe growing larger inside a pre-existing container. It is the increase in distance between points in space, caused by the evolution of the spacetime metric. The fabric itself is stretching. The grid is growing. And that growth does not require an external framework to happen within. It is intrinsic, self-contained. The universe expands because that is what the equations describing spacetime predict it will do. Not because it is pushing into something, because the metric is changing. Now let me push this further, because the paradox is not just about the Big Bang. It is about right now. Space is still expanding. Today, this moment. Distances between galaxies that are not gravitationally bound to each other are growing. New space is appearing in the gaps. The fabric is stretching, and it is not stretching into anything. It is just stretching, becoming more spacious, generating more distance. The process that began 13.8 billion years ago has not stopped. It is ongoing, continuous, relentless, and every second the universe is making more room for itself. Think about what that means. The universe is not a static object. It is not a finished product sitting on a shelf, complete and unchanging. It is a dynamic, evolving structure, a process, a system that creates itself as it goes. Space is not something that was made once and then left alone. It is something that is being made right now. Every moment new distance is generated. Every moment the separation between distant galaxies increases. Every moment the universe grows larger, not by moving into something, but by becoming something larger. The expansion is not an event that happened in the past. It is an event that is happening. Right now, everywhere, all at once. This is the key insight. The universe is not a thing. It is a doing. It is not a noun. It is a verb. Expansion is not something the universe underwent. It is something the universe is. The fabric of space-time is not static. It is active. It stretches. It bends. It ripples. It grows. And all of that activity is self-generated. Space does not need an outside force to push it. It does not need a container to expand within. It expands because that is what spacetime does when it is filled with matter and energy and governed by the equations of general relativity. The universe makes itself. It creates the framework for its own existence, and that framework, spacetime, is not embedded in anything. It is the only thing there is. Now let us connect this to the multiverse. Because if eternal inflation is correct, the process of creating space is not unique to our universe. It is happening everywhere. In regions of space that are still inflating, new volume is being generated at an exponential rate, faster than anything we experience here, faster than light, faster than any motion through space could ever achieve, and within that inflating space new bubbles form. New regions where inflation ends and a hot Big Bang begins. Each bubble is a universe, each one has its own space-time, its own expansion, its own fabric, and each one is doing the same thing our universe is doing. Creating space, making room, expanding into nothing because nothing is what expansion creates. The multiverse, if it exists, is not a collection of universes sitting in a superspace. It is a cascade of self-creating regions, each one generating its own framework, each one expanding intrinsically, without reference to an external container. The bubbles are not floating in a void. They are making the space they occupy. They are defining the distances within themselves, and the inflating regions between bubbles are doing the same thing, creating space, stretching, growing, generating more room for more bubbles to form. The whole structure is self-perpetuating, a process that feeds on itself, that creates the conditions for its own continuation, and none of it requires an outside, because the concept of outside does not apply. Each bubble is its own spacetime. Each one is complete, self-contained, expanding into itself. This is what makes anything possible. Not because the universe is infinite, though it might be, Not because the multiverse produces every possible configuration of matter, though some versions predict that, but because the universe is a system that creates the conditions for existence. It does not sit inside a pre-existing framework, it is the framework, and that framework is dynamic. It grows, it evolves, it makes space for new things to happen, new structures to form, new possibilities to emerge. The expansion of space is not just a fact about the universe, it is the mechanism that allows the universe to be. Without expansion, without the creation of distance, without the stretching of space-time, there would be no galaxies, no stars, no planets, no structure at all. Just a uniform, featureless soup of particles collapsing back in on itself under the pull of gravity. Expansion is what prevents that collapse. It is what allows the universe to grow large enough, and cool enough, and structured enough for anything interesting to happen. The Big Bang did not create matter and energy. Those were already there, in the form of quantum fields, compressed into an unimaginably small region. What the Big Bang created was space, room, distance, separation, the framework within which matter and energy could spread out, cool down, and organize themselves into atoms, molecules, stars, galaxies. The expansion of space is the reason the universe has a history, a timeline, a progression from simple to complex, from uniform to structured, from hot to cold. Without expansion, none of that happens. The universe does not evolve, it does not change, it sits frozen in a single state, crushed under its own density, unable to develop. So when you ask what the universe expanded into, you are asking the wrong question. The universe did not expand into a space that was already there. It expanded into the possibility of space. It created the framework for things to be separated, for events to happen at different times and different places, for there to be a here and a there, a now and a then, a this and a that. Expansion is what makes distinction possible, what makes structure possible, what makes existence in any recognizable form possible. The universe is not occupying space, it is generating it, continuously, relentlessly. And that generation is not happening inside anything, it is the thing that allows inside to mean something. Now let me bring this back to the question of nothing. Because nothing is the word that keeps showing up in this story. The universe expanded into nothing. There was nothing before the Big Bang. The regions beyond the cosmic horizon are separated from us by nothing. And every time the word appears, it confuses the issue. Because nothing does not mean the same thing in all those contexts. Sometimes it means the absence of matter. Sometimes it means the absence of space. Sometimes it means the absence of causality. And sometimes it is just a placeholder for I do not know. The most honest way to use the word nothing in cosmology is to say it means the absence of all physical concepts we can measure or define. Before the Big Bang, if there was a before, there was no space, no time, no matter, no energy, no laws of physics that we recognize. Not because those things were hidden or suspended, because the framework that gives them meaning did not exist yet. You cannot have matter without space to put it in. You cannot have time without events to order. You cannot have physics without a structure for physical processes to unfold within. The Big Bang created that structure. It did not create it out of something. It did not create it in something. It created it as something. The framework itself. The stage. The only context within which the words before and after and inside and outside have any meaning. So nothing in this sense is not a void. It is not a blank canvas. It is the absence of the canvas itself. The absence of the framework, the absence of the possibility of asking the question. An expansion is the process that generates the framework, that makes the canvas. That creates the conditions for questions to be asked and occasionally answered. The universe does not expand into a void, it expands into the creation of space itself. Every moment new distance appears, new separation, new room for things to exist in. And that room is not borrowed from somewhere else. It is not carved out of a pre-existing supply. It is made, generated, brought into being by the evolution of the spacetime metric. This is the paradox revisited. The universe is not a thing in space, it is space. It is not an event in time, it is time. It is the framework within which things happen, events unfold, and existence takes on meaning. And that framework is not static. It is not fixed. It is growing, right now, everywhere, creating more space, more distance. More room for the future to unfold, The expansion is not an accident, it is not a side effect, it is the defining feature of the universe, the thing that makes everything else possible. And it does not require an outside, because outside is a concept that only makes sense within the framework the universe provides. You can sit with that discomfort. You can let your brain twist itself into knots trying to picture a thing that creates the space it occupies, trying to imagine a process that generates the framework for its own existence, trying to reconcile the idea that the universe is not in anything, but is the thing that allows it to mean something. That discomfort is not a sign that you have failed to understand, it is a sign that you are starting to. Because the universe is not built for human intuition. It is not designed to make sense in the way everyday objects make sense. It is stranger, deeper, more fundamental. And the strangeness is not a bug. It is a feature, a direct consequence of taking seriously the idea that space and time are not eternal, unchanging backdrops. They are dynamic, flexible, evolving structures, and those structures create themselves. The paradox dissolves when you stop treating space as a container and start treating it as a thing, a physical, measurable thing that has properties, that responds to matter and energy, that bends and stretches and grows. The universe does not need a container because it is not contained. It is the framework, the only framework, and that framework is making itself, continuously, without pause, without reference to anything beyond itself, because there is no beyond, there is no outside, there is only the universe, expanding, creating space, defining distance, making anything possible by being the thing that allows anything to exist at all. And that brings us to the final question, the one we have been circling since the beginning. If the universe is a self-creating system, if it generates the framework for its own existence, if it expands into nothing because nothing is what expansion makes, then what does that say about us? About our place in this process? About the meaning of existence in a cosmos that requires no outside, no creator, no external cause? That question does not have a scientific answer. It is not about data or observations or testable predictions. It is about what it means to exist in a universe that makes itself. And that is where the next chapter begins. You're standing on a rock, a ball of iron and silicon and oxygen, wrapped in a thin film of water and air, spinning at 1,000 miles per hour, orbiting a medium-sized star at 67,000 miles per hour, being dragged around the centre of a galaxy at 500,000 miles per hour, falling toward another galaxy at 70 miles per second. And all of that motion, every bit of it, is happening inside a universe that is 13.8 billion years old, 93 billion light years across, and expanding faster every moment. A universe that contains roughly 2 trillion galaxies, each one filled with billions or hundreds of billions of stars, scattered across an expanse so vast that light from the farthest edges has been travelling toward you since before the Earth existed and still has not arrived. That is where you are. That is your address. A speck on a rock orbiting an average star in an ordinary galaxy in a universe so large that the part you can see is probably an infinitesimal fraction of the whole. And yet, despite all of that, despite the absurd mismatch between your size and the size of everything else, you are the only thing in that entire cosmos, as far as we know, that can look up at the sky and ask why. That matters. It matters more than the size of the universe, more than the number of galaxies, more than the age or the expansion rate or the fate of everything billions of years from now. Because size is not significance, scale is not meaning. The universe is vast and old and mostly empty, yes, but it is also the thing that made you. The atoms in your body were forged in the cores of dying stars. The oxygen you breathe, the carbon in your cells, the calcium in your bones, all of it came from supernova explosions that scattered the guts of massive stars across space, billions of years ago. You are not separate from the cosmos. You are part of it. A temporary arrangement of stardust assembled by chemistry and evolution, capable of looking back at the process that created you, and understanding, at least in part, how it happened. That is extraordinary. Not because humans are special in some cosmic sense. We are not. There is no reason to think the universe cares about us, or even notices us. We are a side effect. A byproduct of physics and chemistry playing out over billions of years on a planet that happened to have the right conditions. But the fact that we exist at all, that matter can organize itself into structures complex enough to think, to question, to build telescopes and particle accelerators and theories about the origin of everything, that is not nothing. That is the universe becoming aware of itself. A patch of space, 13.8 billion years after it began expanding, developing the capacity to look inward and outward and ask what it is, where it came from, and what it means. And the answer, as you have seen over the course of this video, is complicated. The universe is not a thing, it is a process, a self-creating, self-sustaining system that generates the framework for its own existence. Space is not a container, it is a fabric that stretches and bends and grows. Time is not a river flowing past, it is a dimension, woven together with space into a single structure that expands and evolves. The Big Bang was not an explosion. It was the beginning of spacetime itself, and the expansion we observe today is not motion through a void, it is the creation of distance, the generation of new space. The universe making room for itself by becoming larger. You know all of this now. You have walked through the logic, you have seen the evidence, you have wrestled with the paradox and come out the other side with a picture of reality that is stranger, deeper, and more unsettling than anything your intuition prepared you for. And now, at the end of it all, you are left with a question that science cannot answer. A question that sits at the boundary between physics and philosophy, where data runs out and meaning takes over. What does it mean to exist in a universe like this? Not what does it mean in some grand cosmic sense. The universe does not assign meaning. It does not hand out purpose. It does not care whether you find your existence significant or absurd. Meaning is something you create, something humans do. A way of making sense of the fact that you are here temporarily, in a cosmos that will outlast you by trillions of years and probably does not need you for anything. But the structure of the universe, the way it is built, the fact that it creates itself and expands into nothing and contains within it the raw materials for stars and planets, and eventually life, that structure shapes the kind of meaning you can construct. Because you are not floating in some abstract philosophical void, you are embedded in a physical cosmos, a universe with rules, with history, with a trajectory that started 13.8 billion years ago and is still unfolding. And understanding that cosmos, really understanding it, changes what it means to be part of it. Start with the scale. The observable universe is enormous, 93 billion light-years across, 2 trillion galaxies, more stars than grains of sand on every beach on Earth. And yet, that observable region is probably just a tiny bubble in a much larger structure. If eternal inflation is correct, the total universe is vastly bigger, possibly infinite, filled with regions we will never see, galaxies we will never observe, stars that will never send their light in our direction. The multiverse, if it exists, is even larger. An infinite cascade of bubble universes, each one expanding, each one isolated, each one creating its own space. That scale should make you feel small. It does make you feel small, and that feeling is correct. You are small, microscopically, incomprehensibly small compared to the structure you inhabit. A human lifetime is less than 100 years. The universe is nearly 14 billion years old. You will live for about 100 millionth of the time the cosmos has already existed, and the universe will keep going long after you are gone. Stars will keep burning, galaxies will keep drifting apart, space will keep expanding. The process that began with the Big Bang will continue for trillions of years, indifferent to whether you are here or not. But here is the thing. Small does not mean insignificant. A single neuron in your brain is small compared to your body. A single line of code in a program is small compared to the software it helps run. But the neuron fires, the line executes, and without it, the larger system does not work the same way. You are small in the universe, yes, but you're also part of the process, a piece of the structure. A temporary configuration of matter that can think and question and understand. And understanding, as far as we know, is rare, possibly very rare. Possibly so rare that it only happens in a vanishingly small fraction of the cosmos, on planets where conditions are just right, in galaxies where stars have had time to form and die and seed the space around them with heavy elements. The universe is mostly empty, mostly cold, mostly dark. Most of space is just space, stretching endlessly, with nothing in it but faint radiation and the occasional stray atom. Stars are rare, planets are rarer. And planets with life, with ecosystems, with intelligence, with the capacity to look up and ask why, those are rarer still. We do not know how rare. We have not found another example yet. But the fact that you exist at all means the universe is capable of producing something like you. And that capability, buried in the laws of physics and chemistry, is part of the structure of reality. The same processes that create galaxies also create brains. The same expansion that stretches space also creates the conditions for stars to ignite, planets to form, and chemistry to become biology. You're not an accident in the sense of being a mistake. You're an accident in the sense of being unplanned, a natural consequence of a process that was not aiming for you, but produced you anyway. The universe does not have goals. It does not have intentions. It does not care whether life exists or not. But the fact that life can exist, that matter can organize itself into self-replicating, evolving, thinking structures, tells you something about the kind of universe you live in. It is not a sterile void. It is not a lifeless machine grinding through eternity. It is a place where complexity emerges, where structure builds on structure, where simple rules, applied over billions of years, produce outcomes so intricate and unexpected that they can look back at the process that made them and try to figure out how it worked. That is what you are doing right now, figuring it out, piece by piece, observation by observation. The universe does not explain itself. It does not come with an instruction manual. You have to discover the rules by watching how things behave, testing predictions, building models, and checking whether those models match reality. And the fact that you can do that the universe is comprehensible at all, is one of the strangest and most important facts about existence. Because it did not have to be that way. The laws of physics could have been chaotic, inconsistent, impossible to pin down. The cosmos could have been random, unpredictable, resisting every attempt to find patterns. But it is not. It follows rules. Rules that are the same everywhere, at every time, in every galaxy. And those rules are simple enough, at their core, that a species of hairless primates on a rock in the outer arm of an ordinary galaxy can figure them out. You have figured out that space expands, that time had a beginning, that the universe is 13.8 billion years old, that the observable cosmos contains 2 trillion galaxies, each one a city of stars, scattered across an expanse so large that light takes billions of years to cross it. You have figured out that gravity bends space-time, that black holes exist, that stars fuse hydrogen into helium and die in explosions that seed the universe with carbon and oxygen and iron. You have figured out the cosmic microwave background, the faint afterglow of the Big Bang, and used it to map the conditions of the early universe with precision so high it would have seemed like magic a century ago. You have done all of this in the span of a few hundred years, starting from almost nothing, building on the work of thousands of people who looked up at the sky and refused to accept that it was beyond understanding, and you are not finished. The universe still has secrets, deep ones. Dark energy, the mysterious force driving the accelerated expansion, makes up 68% of the total energy content of the cosmos, and we do not know what it is. Dark matter, the invisible stuff holding galaxies together, makes up another 27%, and we have never directly detected it. The multiverse, if it exists, is forever beyond reach, hidden behind a cosmic horizon we can never cross. The fate of the universe, whether it will expand forever or collapse back in on itself, depends on measurements we are still refining. The measure problem in eternal inflation is unsolved. Quantum gravity, the theory that should describe space-time at the smallest scales, does not exist yet. We have pieces, we have candidates, but we do not have the answer. That is not a failure, that is the frontier. The edge of knowledge, the place where what we know meets what we do not, and the questions start piling up faster than the answers. Science does not end when you solve a problem, it expands. Every answer opens up new questions, every discovery reveals new mysteries. The cosmic microwave background confirmed the Big Bang, but it also showed us that the early universe was filled with tiny fluctuations we did not predict. Measuring the expansion rate solved the question of how old the universe is, but it created the Hubble tension, a disagreement between methods that might signal new physics. Discovering dark energy explained why distant supernovae look the way they do, but it raised the question of what dark energy actually is and why it has the value it does. You could see that as frustrating, an endless treadmill of questions with no final answer in sight. Or you could see it as the point. Because the universe is not a puzzle with a solution sitting at the end waiting to be unlocked. It is a structure, a process, an evolving system that we are part of and trying to understand from the inside. And understanding, real understanding, is not about reaching a destination. It is about building better maps, asking sharper questions, refining the models until they match reality with higher precision. The fact that there are still mysteries does not mean we have failed. It means the universe is deeper than we thought. And deep is good. Deep means there is more to discover, more to learn, more room for the next generation of scientists to push the boundary a little farther and see what is waiting on the other side. Here is what we know about the future. The universe will keep expanding. For now, that is certain. The galaxies we see today are moving apart. The space between them is growing. And because dark energy dominates the total energy budget, the expansion is accelerating. Galaxies that are not gravitationally bound to us are receding faster every year. Eventually, they will drift beyond the cosmic horizon. Their light will be redshifted into undetectability. And future observers, billions of years from now, will look out at a much emptier sky than we see today. In a few 100 billion years, long after the sun has exhausted its fuel and died, the observable universe will have shrunk down to a handful of galaxies, the local group bound together by gravity, immune to expansion. Everything else will be gone, not destroyed, just hidden, pushed so far away by the stretching of space that no light from those regions can ever reach us again. The cosmic microwave background will have faded into noise, the evidence for the Big Bang will be gone, and any civilization that exists at that point will have no way to reconstruct the history of the cosmos. They will be trapped in a dark, quiet universe with no indication that it was ever anything else. That future is strange, but it is also far away. Right now, in this era, the universe is still young enough and dense enough that we can see the evidence. We can measure the expansion. We can detect the cosmic microwave background. We can map the large-scale structure of the cosmos and trace its history back to the Big Bang. We live in a golden age of cosmology, a time when the data is good, the questions are sharp, and the answers are starting to come into focus. Not all the answers, not the final answers, but enough to build a coherent picture of where we came from and where we are going. And that picture is this. The universe began as an unimaginably small, hot, dense state. Space and time came into existence together. The initial expansion, possibly driven by inflation, stretched space to enormous scales in a fraction of a second. The inflaton field decayed, converting its energy into particles. The universe cooled. Protons and neutrons formed. Hydrogen and helium condensed in the first few minutes. Atoms formed when the universe was 380,000 years old. Gravity pulled matter together into clumps. The first stars ignited, galaxies assembled, stars lived and died, enriching space with heavy elements. Planets formed. On at least one of those planets, chemistry became biology. Biology became complexity. Complexity became intelligence, and intelligence became you. Standing on a rock, looking up at the sky, asking how it all happened. That is the story. Not complete, not finished, but true as far as we can tell. Built on evidence, tested against observation, refined over decades by thousands of researchers working in dozens of countries, using instruments that can detect light from galaxies billions of light years away, and ripples in space-time so faint they shift mirrors by a distance smaller than a proton. The story is solid, and it is strange, because the universe is not what common sense would predict. It is not static. It is not eternal in the way people once assumed. It had a beginning. It is expanding. It is accelerating, and it creates itself as it goes, generating the space and time and structure that allow anything to exist at all. You are part of that process. A temporary arrangement of atoms, assembled by the same forces that built galaxies, governed by the same laws that describe black holes and the cosmic microwave background. You're not separate from the universe, you're an expression of it. A way the cosmos has found, at least in this corner of space, to look at itself, to ask questions, to build models, to test predictions, to map the structure of reality and understand, at least partially, how it works. And that understanding comes with responsibility, not cosmic responsibility. The universe does not care what you do, but human responsibility. Because the knowledge we have built, the picture of the cosmos we have assembled, is fragile. It depends on institutions, on funding, on education, on the willingness of societies to support people who spend their lives staring at distant galaxies and trying to make sense of the data. That knowledge is not guaranteed. It can be lost. It has been lost before, in other times, in other places, when civilizations collapsed and libraries burned and the accumulated wisdom of generations disappeared. The universe will keep expanding whether we understand it or not. But the understanding itself, the ability to look up and see not just points of light but galaxies, to measure not just distances but the history of spacetime, to ask not just where but why, that is something we have to maintain. It is not automatic, it is work, and it is worth the work. Because the alternative is to live in ignorance, to look up at the night sky and see mystery instead of structure, to accept that the universe is beyond comprehension, that the questions are too big, that we are too small to ever figure it out. That attitude is understandable. The cosmos is vast, the questions are hard, and human lifetimes are short. But the fact that the questions are hard does not mean they are unanswerable. It just means the answers take time. Generations, centuries, a continuous effort to build on what came before, refine the models, collect more data, and push the boundary of knowledge a little farther. You are living in the middle of that effort, not at the beginning, not at the end. Somewhere in the middle of a process that started when the first humans looked up at the stars and wondered what they were, and will continue as long as there are humans, or anything like humans, capable of asking questions and testing answers. The picture is not complete, it will never be complete. Because the universe is not a static thing you can finish understanding. It is a process, an evolving structure. And the more you learn about it, the more questions emerge. But here is what you can say with confidence. The universe is real. It is knowable. It follows rules. Those rules are the same everywhere, and they can be discovered by observation and experiment. The cosmos had a beginning. It is expanding. It is creating space as it grows. It does not need a container. It does not need an outside. It is the framework within which everything happens. And that framework, strange as it is the only one there is. You are part of it. You are made of it. And for a brief moment, a tiny fraction of cosmic time, you are aware of it. Capable of looking up, looking inward, and asking how it all fits together. That awareness is the ultimate frontier, not the edge of the observable universe. Not the boundary where our telescopes run out of light to detect. The frontier is the gap between what we know and what we can know, between the data we have and the questions we can ask, between the models we build and the reality they try to describe. That frontier is always moving. Every discovery pushes it back a little. Every answer creates new questions. And every generation of scientists hands the map to the next, saying, "We made it this far. See how much farther you can go." You're standing on a rock in a universe that is 13.8 billion years old, 93 billion light years across, and expanding into nothing because nothing is what expansion creates. You are made of atoms forged in the cores of stars that died billions of years ago. You are capable of understanding, at least in part, the process that made you, and you are living in an era when the evidence is still visible, the data is still accessible, and the questions are still sharp enough to pursue. That is not everything. But it is something rare, something worth holding on to, something worth passing on. The universe does not care whether you exist, but you exist anyway. And for as long as you do, you have the capacity to look up, look out, and ask why. That capacity is not nothing. It is the thing that makes the vast, cold, mostly empty cosmos feel, for a moment, less lonely. Because somewhere in the expanse, on a rock orbiting an average star, a patch of organized matter looked back at the process that created it and understood. Not completely, not perfectly, but enough. Enough to know that space is a thing, that time had a beginning, that the universe is a self-creating system, that expansion does not require an outside, and that you, temporary and small as you are part of the story. A footnote, maybe. But a footnote written in atoms forged by stars, asking questions the universe does not answer but allows you to ask. And that in the end, is the only meaning that matters. So here we are, at the end of a story that has no ending. You came here with a question that sounded simple. What did the universe expand into? And now, 300 words from the finish line, you know the answer is not simple, it is not comforting, and it is not the kind of answer that closes the book and lets you walk away satisfied. The universe expanded into nothing because there was no into. Space is not a container. It is the thing being created. The Big Bang was not an explosion at a point, it was the ignition of space-time itself. Expansion is not motion through a void, it is the generation of distance where no distance existed before. The cosmos does not sit inside a larger framework, it is the framework, the only one there is, and it makes itself, continuously, without reference to anything beyond. Because there is no beyond. That answer should unsettle you. It unsettles everyone. Because your brain was not built to handle a reality that creates its own context. You want a stage, a room, a place where the universe happens. But the universe is not happening inside something. It is the something. And recognizing that, really accepting it, means letting go of the idea that existence requires permission. The cosmos does not need a cause. It does not need a container. It simply is, and it keeps being. Right now, this moment, space stretching, time unfolding, distances growing. The process that began 13.8 billion years ago still running, indifferent to whether you understand it. You're standing in the middle of that process, made of it, shaped by it. A temporary pattern in the fabric asking questions the fabric does not answer. And the strangest part, the part that makes all of this worth thinking about, is that the universe allows the question to be asked at all. It built you. It gave you eyes and a brain and the capacity to look up and wonder why. Not because it needed to, but because the rules permit it. And for a brief flicker of cosmic time, you are here. Awake, aware, staring at the edge of everything you can ever know and realizing the edge is not a wall. It is a horizon. And beyond that horizon is more. Always more. Forever out of reach. Forever real. The universe expanded into nothing, and nothing, it turns out, is exactly what makes everything possible.